This question is about particle physics. The question says, an isotope of potassium 4019K is used to date rocks. The isotope decays into an isotope of argon, Ar, mainly by electron capture. So electron capture is the decay mode. The decay is represented by this equation. The equation is 4019K plus 0 minus 1e goes to unknown mass number, unknown atomic number, argon, plus an unknown product. So in order to answer this question, we're going to use three things. We're going to use that we know what electron capture is. So electron capture. We're going to use that charge must be conserved. And finally, we're going to use that lepton number is conserved. Lepton number. Okay. So first we use the definition of electron capture, which is that electron capture constitutes a proton absorbing an electron to become a neutron. So in this process, the mass number remains the same. So in other words, the proton that has become a neutron is in the nucleus of the potassium, and so the mass number of the potassium remains the same, but because a proton has become a neutron, its atomic number must have decreased by 1. Okay, so that's our first mark. Our second mark is for the other product, and so we can use the fact that this is an equation, so the sum of the mass and atomic numbers, or charges rather, on the left-hand side is equal to the same thing on the right-hand side. So essentially we have 40 plus 0 on the left is equal to 40 plus something else on the right, which means the mass number has to be 0. And secondly, we can use that 19 plus minus 1 is 18, which means that also the charge of the other product has to be 0. Here we've used that charge is conserved to say 19 minus 1 is 18 plus 0. Okay. So finally, we have to figure out what the final product is. And at this point, it could either be a photon, which has 0 mass and 0 charge, or an electron neutrino or an electron antineutrino. So in order to figure out which it is, we have to use that the lepton number is conserved. And so this means that we have the same number of leptons/antileptons on the left-hand side as right-hand side. So every lepton has a lepton number of +1, and every antilepton has a lepton number of -1. So in this case, we have one electron, so that's a lepton number of +1 on the left-hand side, which means we have to have a lepton number of +1 on the right-hand side. And as a result, we need an electron neutrino, because this also has a lepton number of +1. A photon has a lepton number of 0, because it's not a lepton, and an electron antineutrino has a lepton number of -1, so it wouldn't be suitable here. And indeed, if you put an electron antineutrino, you don't get the mark here. So we had 1 mark for getting the correct numbers for argon, and 1 mark for getting the electron neutrino. The next part of the question says, explain which fundamental interaction is responsible for the decay in question 1. And so generally when we're dealing with particle physics, we're not interested in gravity because it's way too weak. So we're left with the strong interaction, the weak interaction, and the electromagnetic interaction. So it can't be the electromagnetic interaction because one of the products of the decay is a neutron, and a neutron is not charged, and the electromagnetic interaction is only between charged particles and photons. So that's no good. Secondly, we could potentially have the strong interaction, but that's no good because the decay puts out a lepton and involves an electron coming in, which is also a lepton. So as a result, it can't be the strong interaction because that only involves hadrons. So we're left with the weak interaction, which works because this is an interaction between hadrons and leptons. So the answer is weak interaction, because the interaction is between hadrons and leptons. The next part of the question says, one decay mechanism for the decay of 1419K results in the argon nucleus having an excess energy of 1.46 mega electron volts. It loses this energy by emitting a single gamma photon. So photon. Calculate the wavelength of the photon released by the argon nucleus. So there are a few things going on in this question. Firstly, we've been given our energy in mega electron volts, and to use most of our equations, we'll need to convert things to SI units. So in order to do that, we can write the energy, E, is equal to 1.46 mega electron volts. Now, that's equal to 1.46 times 10 to the 6 electron volts. I've just used the prefix mega, which is 10 to the 6. And then we can use the definition of the electron volt, which is that 1 electron volt is 1.60 times 10 to the minus 19 joules to three significant figures. So we can write that the energy in joules is 1.46 times 10 to the 6 times 1.60 times 10 to the minus 19 joules. And that's our first mark. Our second mark is for identifying and using the correct equations in order to form an expression for the wavelength. So the two equations we're going to need is we want one equation that relates the energy to the frequency of the photon. So that equation is E is hf, where E is the energy, h is Planck's constant, and f is the frequency. And our other equation relates the wave speed, c, which is just 3 times 10 to the 8 meters per second, because we're dealing with electromagnetic radiation, and they all have that speed in a vacuum. And that's equal to the product of the wavelength and the frequency, f, lambda times f. Okay, and so we want to relate the wavelength to the energy. So to do that, we can rearrange the expression for the energy to make the frequency the subject. So the frequency is E divided by h. And then secondly, we can substitute in this into c as f lambda. So in other words, we can write c is equal to E lambda divided by h. And then we multiply by h and divide by E to make lambda the subject. In other words, lambda is hc divided by E, like so. Okay, at this point, all we need to do is put in our numbers to get that second mark, and our third mark will be for the correct numerical answer. So Planck's constant is just 6.63 times 10 to the minus 34 to three significant figures, and the speed of light is just 3 times 10 to the 8. And then finally, what we have is the energy from above, so 1.46 times 1.6 times by 10 to the 6 times by 10 to the minus 19, like so. And that gets us a wavelength of 8.51 times 10 to the minus 13 meters. So our final mark is for that. Note that we can do a bit of a sanity check here. Because we're dealing with a gamma ray, we expect a wavelength that's very small. And the range for the wavelength of a gamma ray is around 10 to the minus 15 to 10 to the minus 13 meters. So it's comforting to know that we're about the right wavelength. The final part of the question says, the potassium isotope can also decay by a second decay process to form a calcium-40 nuclide. And they want us to suggest how the emissions from a nucleus of a decaying potassium can be used to confirm which decay process is occurring. So to answer this question, we should try and identify what decay it is to form the calcium-40 nuclide. So we can write an equation, which is that we have 40 and then 19K goes to 40, 20 calcium plus some products, which we'll need to figure out. So in order to figure them out, we can use that the mass numbers on each side have to add up. We can use that the atomic numbers, or the charges rather, on each side have to add up. And then we'll use conservation of lepton number and baryon number, or specifically in this case, lepton number. So because we have 1419 and 1420, we know that we're going to have products with a leftover charge of -1. So that could be one particle. And we know that its mass has to be 0. So a particle that fits the bill is the electron, like so. And then, because we now have a lepton number of +1 on the right-hand side, but 0 on the left-hand side, it means we have to have another lepton that balances it out. Note that this other lepton can't have a charge, because otherwise the charges wouldn't balance on the left and right-hand side. and it can't have a mass either because the masses also have to balance. So in this case, the only thing that fits the bill is an electron antineutrino. Now this time it's an antineutrino because we want the lepton number +1 from the electron to cancel with whatever lepton we have here, and an antineutrino has a lepton number of -1. Okay, so for our first mark then, all we need to say is that this is a beta minus decay. Since that's the equation we've just come up with up here, we've released a negative electron, therefore it's beta minus. Secondly, we can say that because it's a beta minus decay, an electron is released. And so to get the final mark, so the first mark was for the beta minus decay, the second was for saying that an electron is released, we can talk about a few different things. We can either talk about how we detect the electron, for example, using a cloud chamber or by absorption by a nucleus, or we could say what other products are released, an antineutrino in this case, an electron antineutrino, or finally, we could say that there's no photon released in this decay, whereas in the other decay mentioned earlier in the question, a photon was released. In this case, I'm just going to say that an antineutrino is also released. This question is about vibrations on a string. It says, Figure 1 shows an arrangement used by a student to investigate vibrations in a stretched nylon string of fixed length L. He measures how the frequency F of the first harmonic vibrations for the string vary with the mass m suspended from it. So what we see here is a string held at one end. The bridge can be moved, which changes the fixed length L, and then the string is put over a pulley, and then there's a tension applied to it using the masses. So immediately, what we can say is that the tension in the string has to be equal to the weight of the masses. The reason for this is that if we consider the forces acting on the masses, we know that we have their weight, and then they must be suspended and not moving, so there must be an upward force that comes from the tension in the string. Now, because the masses are in equilibrium, i.e. they're not moving, we just have that T has to be equal to mg. The question goes on to state the results of the experiment. So for given pairs of the mass applied to the string, the frequency is given by this. So for example, with mass 0.5 kilograms, we have a frequency of 110 hertz. So I'm just going to label these as 1, 2, and 3 because we're going to refer to it later. So the question wants us to show that the data in table 1 are consistent with the relationship F is proportional to the square root of T, where T is the tension in the nylon string. So firstly, for two things to be proportional, what it means is that I can write the quantity, in this case F, is equal to a constant, which I'll call K, and this isn't the spring constant, this is just a number, multiplied by the square root of T. So what that means is that now I can consider frequencies and tensions at two different points. So for example, imagine I have at one point a tension T1 and F1, so one tension and one frequency, and then at another point I have T2 and F2, another tension and another frequency. And so that means that for F1, I can write that F1 is equal to K multiplied by the square root of T1, and for F2, I can write that F2 is equal to K, the same number, multiplied by the square root of T2. So now if I divide F2 by F1, then what I'm left with is the square root of T2 divided by the square root of T1, since the K's have cancelled in the fraction, leaving me with square root T2 over T1. This means that if we can show that F2 over F1 for two different points is equal to the square root of T2 divided by the square root of T1 at these two different points, then I've shown that the quantities are proportional to each other. So that's what we're going to do. Now, we can also use what we know about the tension, specifically that the tension in the string just has to be given by mg. We said that earlier. So we can rewrite this relationship F is proportional to the square root of T as F is proportional to the square root of mg, which, since g isn't changing, it's just the acceleration due to gravity, and it's a constant on the surface of the Earth, we can say that the frequency that the string vibrates at is proportional to the amount of mass that's applied to the string. So now let's do this calculation for our different data points. So let's do 1 and 2 first. So for the masses, the ratio of the square roots of the masses, we have m2 divided by m1, and that's equal to 1.26, and that's equal to 0.8 divided by 0.5 all square rooted, which is equal to 1.264 with more numbers after it. And then for the frequencies, we can do f2 divided by f1, and that's just equal to 140 divided by 110, which is equal to 1.273 ... And then to two significant figures, which is the precision that the data is given to in the questions. That's what we have to round our final answer to. We can say that this is equal to 1.3, and this is approximately equal to 1.3 as well, to two significant figures. So let's do the same thing for points 1 and 3. So 1 and 3. And we find that the ratio of the square roots of the masses, m3 divided by m1, is equal to the square root of 1.2 divided by 0.5, which is equal to 1.548. And then for the frequency, we have f3 divided by f1, which is equal to 170 divided by 110, which is equal to 1.545. And again, this is approximately equal to 1.5 for the same argument where we have to round to two significant figures, and this is approximately equal to 1.5 as well, like so. Okay, so now we can say that the square root, that these two ratios are the same, and therefore we can say that f is proportional to the square root of t. So to finish this question, we just need to write a conclusion, which is to say that the square root of the masses, the ratio of the masses, is equal to the ratio of the frequencies. Therefore, f is proportional to square root of m, which is proportional to the square root of t. The next part of the question says, the nylon string used has a density of 1,150 kilograms per meters cubed and a uniform diameter of 5 times 10 to the minus 4 meters. So notice here that they've given us the diameter and not the radius of the string, which is a common mistake that people make to confuse the two. And so the question wants us to determine the length L of the string used. So in order to answer this question, we're going to need two equations. We're going to need the equation which relates the density of a substance to its mass and its volume. Rho is m over v. We're going to need that the frequency of the first harmonic, and this is why it was important that we're dealing with the first harmonic, as it said in the question, is equal to 1 over 2 times the length of the string that's constrained to vibrate, times by the square root of the tension divided by the linear density. And this is what we're going to combine together. So first, a note on the difference between rho and mu. So rho is the density, and it tells you how much of a mass of something you have in a given volume, whereas mu tells you about how much stuff you have in a given length. In other words, I've multiplied through by the area to do this. So I can see this by writing rho is equal to mu times by L. So mu is the linear density, how much stuff I have in a length, times by that length, by a length, L. And then I can rewrite the volume as the area of the object, the cross-sectional area, times by the length. So the L's cancel here, and I'm left with rho is equal to mu divided by A, which is the equation we're going to use in a second. Okay, so then our first mark is for calculating the linear density mu correctly. So what we're going to say is that our wire looks like a cylinder, like so, with a cross-sectional area given by pi times the radius of that circle squared. So the radius is just half the diameter, so our area is going to be given by a pi times 5 times 10 to the minus 4 divided by 2 all squared. So here d is 5 times 10 to the minus 4, the diameter, and then I've divided it by 2 to get the radius, and then substituted it into the formula for the area, pi r squared. Okay, so then we can use that to calculate the linear density mu. So mu is equal to rho times by a. So substituting in the numbers we were given in the question, rho is given by 1150, and a is given by this expression I've just written down over here. So pi, and let me just box that off, times by 2.5 times 10 to the minus 4 all squared. And that gives us roughly 2.258 times 10 to the minus 4 kilograms per meter. Okay, so that was the first step. The second is that we want to use our equation, F is 1 over 2L, multiplied by the square root of T divided by mu. And firstly, we'll want to rearrange this for L. So to do that, we multiply both sides by L and divide both sides by F, which gives us L is equal to 1 over 2F multiplied by the square root of T divided by mu. Okay, so next we need to use what we know about T, specifically that it's just equal to the weight of the masses applied to the string. And so we get 1 over 2F into mg divided by mu, like so. Okay, so at this point, we can pick any of our data points from previously in the question, specifically either 0.5 and 110, 0.8 and 140, or 1.2 and 170, and use that to get our final answer for L. So at this point, I'm just going to use 110 and 0.5. So therefore we can write L is equal to 1 divided by 2 times 110, the frequency, multiplied by the mass applied at that frequency. So 0.5 times by the acceleration due to gravity, 9.81, divided by the value we calculated for mu further up in the question, 2.258 times 10 to the minus 4. I'm rearranging that equation to get the right form for L, and then substituting the numbers in gets us our second mark, and our third mark is for a correct final answer, which is 0.669938 which, if you round to two significant figures, gives you 0.67 meters. And that's our answer, 0.67 meters. In the final part of the question says, the student uses the relationship in question 1 to predict frequencies for tensions that are much larger than those used in the original experiment. Explain how the actual frequencies produced would be different from those that the student predicts. So what's going to happen for the string is that as you stretch it, actually the area is going to decrease, the cross-sectional area. This is because the diameter is decreasing as you pull it apart, if you exert large tensions on it. Eventually, at some point, if you kept pulling on it, the string would snap. So the point is that actually the linear density mu, which, remember from the previous question, depends on the area, what we realize then is that because the diameter is decreasing, we also expect the frequencies to increase, because F is proportional to 1 over the square root of mu. and mu is decreasing because the area is decreasing. Therefore, all we need to say is that because the diameter is decreasing, the actual frequencies produced would be larger. This question is about refraction of light. The question says, Figure 2 shows a ray of monochromatic green light, so monochromatic means all the same wavelength, incident normally on the curved surface of a semicircular glass block, like so. They tell us that the angle of refraction of the ray at the plane surface is 90 degrees. So we can add that to our diagram by drawing on the normal, like so. So 90 degrees is a right angle. They also tell us that the refractive index of the glass used is 1.6. And they want us to calculate the angle of incidence of the ray on the flat surface of the block. So firstly, since the light ray is incident normally to the glass block, it doesn't change direction as it comes in. It reaches the center point here, which is also at the boundary of the glass block, and then comes off at a right angle like we're told in the question. In order to solve this then, we need to use the relation between the refractive indices of two materials and the angles of incidence and the angles of refraction. Specifically, n1 sine theta 1 is equal to n2 sine of theta 2, where n1 is the refractive index of the first material, n2 is the refractive index of the second material, theta 1 is the angle of incidence, and theta 2 is the angle of refraction. So adding those to our diagram, what we have is that theta 1 is this angle here. It's the angle at which the light ray comes in towards the normal at the point where it hits the surface. Theta 2 is just this right angle. N1 is just the refractive index of the glass, and N2 is the refractive index of the air that the ray is coming into. So then using N1 sine theta 1 is equal to N2 sine theta 2, with theta 2 equal to 90 degrees. What we can say then is that since sine theta 2 is 90 degrees, sine of theta 2 is sine of 90 degrees, which is equal to 1. Then what we can say is that N2 is about 1. It's actually air rather than a vacuum, so it's not quite 1, but it's 1.00 and then some numbers. So essentially it's 1. We know what N1 is. That's just the refractive index of the glass, and that's given to us as 1.6. So we can say that sine theta 1 is equal to N2 divided by N1, which is equal to 1 divided by 1.6. So finally, we can write that theta 1 is equal to sine inverse of 1 divided by 1.6, which is just equal to 38.682 ... which is equal to 39 degrees to two significant figures, which is the degree of precision that the data in the question is given to. So this is 39 degrees. Since it will be important for later, note that what we've calculated here is actually the critical angle, because the critical angle is the last angle where a light ray can come in and still come out of the block at all, and it comes out at 90 degrees. If the angle was any larger, then we would get total internal reflection, and if the angle was any smaller, then the light ray would come out at an angle smaller than 90 degrees. The next part of the question says, a thin film of liquid is placed on the flat surface of the glass block as shown in figure 3. So there's the film of liquid. The angle of incidence is changed so that the angle of refraction of the green light ray at the glass liquid interface is again 90 degrees. So in this case, they've just modified the angle that it comes in at such that we still get coming out at 90 degrees. And they want us to again calculate the refractive index and this time they want us to calculate the refractive index of the liquid. So in order to do that, we can again mark on our normal, we can mark on our theta 2, like so. Or rather, I'll draw it with an arrow. We can mark on θ1, like so. And then we can just apply the same equation that we used in the previous part. So specifically, we can write that n1 sine θ1 is equal to n2 sine θ2. And this time, we are interested in calculating the refractive index of the liquid. So n1 is again the refractive index of the glass, and n2 is the refractive index of the liquid. So what we need to do is rearrange for n2, the refractive index of the liquid. So doing that, we can substitute in that θ2 is again 90 degrees. So sine of θ2 is sine of 90 degrees, which is just equal to 1 like before. And we know what the value of n1 is because it was given to us in the previous part of the question. And we're told that the angle of incidence θ1 is 58 degrees. So we calculate the value of n2 to be 1.35687 ... which is 1.4 to 2 significant figures. And so that's our answer. So in this question, our 2 marks were for firstly, getting a correct expression for n2 in terms of the refractive index n1, 1.6, and the incident angle 58 degrees, and our second mark was for a correct numerical answer of 1.4. The final part of the question says, the source of green light is changed for one that contains only red and blue light. So that's 2 wavelengths. For any material, red light has a lower refractive index than green light, and blue light has a higher refractive index than green light. They tell us that the angle of incidence at the glass-liquid interface remains at 58 degrees. And the question wants us to describe and explain the paths followed by the red and blue rays immediately after the light is incident on the glass-liquid interface. So, in order to do this question, we need to understand what the effect of changing the refractive indices is on the angle that the light ray comes out at. So, we can consider 3 different situations. We can consider one where we have our block like this, we have a light ray that comes in, and then it comes out at some angle, like so. We can consider the case that we dealt with in the previous parts of the question, where we have a light ray that comes in, and then it comes out at 90 degrees, like so. Or finally, we can consider the case where we have our light ray that comes in, but it's come in at such a steep angle that we get total internal reflection. And so it reflects rather than going out at the point where it first hits the glass liquid boundary. Okay. So to get our 3 marks, we first need to say we do not know by what factor the refractive indices change. For example, they could change like in the first case over here or the second case. So we do not know by what factor the refractive indices change. So we cannot predict the impact of changing the refractive indices on the critical angle, and thus we cannot predict how the path of the light rays change. So the first mark for saying that we can't predict by what factor the refractive indices change, the second for saying that we can't predict the effect on the critical angle, and the third for concluding that because of that, we can't predict the effect on the light ray, on the path of the light rays. This question is about internal resistance. The question says, an engineer wants to use solar cells to provide energy for a filament lamp in a road sign. The engineer first investigates the EMF and internal resistance of a solar cell under typical operating conditions. The engineer determines how the potential difference across the solar cell varies with current, and their results are shown in the graph figure 4. In the graph, we see a linearly decreasing relation between the potential difference across the solar cell and the current through the solar cell. The question goes on to say, the engineer uses the graph to deduce that when operating in typical conditions, a single solar cell produces an EMF of 0.7 volts and has an internal resistance of 8.0 volts, or 8.0 ohms. The question wants us to explain how the engineer uses the graph to obtain the values for the EMF and internal resistance of the solar cell. So to answer this question, we need to relate the potential difference across the solar cell to the current and the internal resistance and the EMF. To do that, we draw a circuit diagram where we treat the solar cell just like a cell with some internal resistance R, and then there will be some load connected across the solar cell that has a different resistance, big R. So the EMF is the potential difference generated by the cell, and V is the potential difference that would be recorded by a voltmeter that we place across R. So we can apply the Kirchhoff's laws to this, and specifically what we want to say is that the EMF is equal to the current times by the resistance of the load plus the current times the internal resistance. So this value here is V, and this is the voltage across and the I times little r is the voltage across the internal resistance. So we can then rearrange this equation such that we have V is equal to epsilon, the EMF, minus the current times by the internal resistance. So what we end up seeing is that the voltage is related to the current by this equation, and this is in the form of a straight line. In such a straight line, the EMF would be the y-intercept, and little r, the internal resistance, would be the negative of the gradient. So to get the marks, we need to say for 1 mark that the EMF is the y-intercept of the graph, and the internal resistance is minus the value of the gradient for the other mark. The next part of the question says, to operate effectively, the lamp in the road sign needs a minimum current of 75 milliamps. At this current, the resistance of the filament lamp is 6.0 ohms. The engineer proposes to try the 2 circuits shown in figure 5, where we have a solar cell connected directly to the road sign of resistance 6.0 ohms, and the more complicated figure 6, which has one cell connected in series with a parallel combination of 2 other cells, which are all connected directly to the road sign of resistance 6.0 ohms. The question then states, deduce, using calculations, whether the circuits in figure 5 and figure 6 are suitable for this application. So, in order to answer this question, we need to analyze both the circuit in figure 5 and the circuit in figure 6. First, looking at the circuit in figure 5, we can rewrite this as an equivalent circuit because the solar cell that we're dealing with is really just a cell with an internal resistance and an EMF, just like we discussed earlier in the question. So, what we have then is a cell connected in series to the road sign, which is just a resistor of resistance 6 ohms, which also has an internal resistance that we found out earlier in the question, which was 8 ohms. The internal resistance of the cell, the EMF of the cell was 0.7 volts, as we found out before. So from this, we can use our equation that relates the potential difference across the cell to the EMF and to the internal resistance to work out what the current in the circuit is. Our strategy is going to be that if the current is large enough to satisfy the requirement of being greater or equal to 75 milliamps, then the circuit will work. Otherwise, the current is not large enough, and so we will be unable to conclude that the circuit works. So for figure 5, what we find is that the potential difference across the road sign V is equal to minus Ri, the internal resistance multiplied by the current, plus the EMF. Now we then apply Ohm's law, so we use the fact that the potential difference across the road sign is equal to the current through the road sign multiplied by its resistance, which we're also given. Since we needed to solve for the current in the circuit, and so we needed an equation that related the potential difference across the road sign to the total current in the circuit I. And that gives us IR is equal to minus Ri plus epsilon. Then we need to rearrange to make I the subject. So add little r times I to both sides to get I times R plus little r is equal to the EMF, and then divide through by big R plus little r to get I is equal to big R plus epsilon divided by R plus little r. So substituting in the values that we got, we know that the EMF of one cell is 0.7. We know that the resistance of the road sign is 6 ohms or 6.0 ohms, and we know that the internal resistance is 8.0 ohms. So substituting those in, we get that the current is 0.05 amps, which is 50 milliamps. And 50 milliamps is less than 75, so this circuit is not suitable. As for figure 6, in order to tackle this, we need to make sense of these solar cells. So as we used earlier in the question, we can think of these solar cells as just a cell connected to an internal resistance, with the internal resistance being 8 ohms and the EMF of the cell being 0.7 volts. So if we analyze this parallel combination first, what we have is a cell with an internal resistance connected in parallel to a cell with another internal resistance. Now, the thing to notice about this is that both cells have an EMF of 0.7 volts, and the internal resistances are the same. So what this is acting like is a cell in series with a parallel combination of the internal resistances. So in other words, this parallel combination of cells is the same as a diagram like this. But then we need to know what that resistance is, and to do that, we combine the resistors in parallel, the internal resistances. So I'll call the resistance of that R parallel, and that resistance is given by the equation 1 over R parallel is equal to 1 over an internal resistance plus 1 over another internal resistance, because both these have the same internal resistance, little r, which is 8 ohms. So putting that in, what we have is that 1 over R parallel is equal to 2 over 8. So therefore, R parallel is equal to 4 ohms. So the point is, by connecting these two cells in parallel, we get an equivalent circuit where the cell that you have is the same. It has an EMF of 0.7 volts, but now the resistance is halved because I've added the internal resistances in parallel. So in order to make sense of the full circuit then, we just need to incorporate this parallel combination into it. So we had the road sign, which acts as a resistor, a 6 ohm resistor. We have the other solar cell, which wasn't in the parallel combination, and that had an internal resistance of 8 ohms, and then otherwise acts like a cell of EMF 0.7 volts. Then we also had the parallel combination, which we reduced to just an equivalent circuit with an internal resistance of 4 ohms, and then another cell, which still had an EMF of 0.7 volts. And so what we see is that we can then say that the total EMF here is 1.4 volts because we just add the EMF from each of the cells, and the total internal resistance is 12 ohms. From adding the two resistors in series with each other, the two internal resistances, the 4 ohms and the 8 ohms. So far in this question, we got 1 mark for determining that figure 5, the circuit in figure 5, wasn't suitable. We'll get our remaining marks from talking about figure 6. So we get 1 mark for saying that the EMF in figure 6 is 1.4 volts, like we just worked out. We get another mark for saying that the internal resistance in figure 6 is 12 ohms. And then we'll get our final mark from applying the same equation that we used for figure 5 with the new values of the EMF and the internal resistance that we worked out. So in the same way as before, we can write down that I is equal to the EMF. So the current is equal to the EMF divided by the resistance of the road sign plus the internal resistance of the circuit. So in that case, this is 1.4 over 6 plus 12. And so if you do that calculation, then you end up with a current of 0.078 amps, which is just 78 milliamps by multiplying by 10 to the 3 to convert amps to milliamps. And so 78 milliamps is greater than 75 milliamps. So the circuit in figure 6 is suitable. And that's our 4th mark. The final part of the question says, solar cells convert solar energy to useful electrical energy in the road sign with an efficiency of 4%. So in other words, that would be 0.04. The solar cell supply used by the engineer has a total surface area of 32 centimeters squared. The question wants us to calculate the minimum intensity in watts per meter squared, so different unit than the different unit of area than has been supplied to us in centimeters squared, of the sunlight needed to provide the minimum current of 75 milliamps to the road sign when it has a resistance of 6.0 ohms. So in order to do this, we're going to work backwards. So our strategy is going to be to calculate the power dissipated in the road sign, calculate how much solar energy we've obtained overall, and then using the efficiency, we'll do that using the efficiency, and then finally we can convert that to an intensity. So the equations we're going to need are P is I squared times R, where I is the current through the road sign and R is its resistance. And we're going to need the equation that relates intensity to the power. So intensity, solar intensity is equal to the solar power divided by the area that captures it. Okay, so let's start by calculating the power dissipated in the road sign. So in this case, we know that the current is 75 milliamps, and we know that the resistance is just 6.0 ohms. So we can write that 0.075. So I've converted the 75 milliamps back to amps because we're using SI units. So 0.075 all squared times by 6 gives us the power dissipated in the road sign, and that's 0.03375, and that's in watts. From there, so this is power dissipated in road sign. Okay, so now we want to calculate the power received, or solar power received, and that's going to be equal to 0.03375 divided by 0.04. So the way to think about this is that we started with a certain amount, and then we multiplied by 0.04, that was our efficiency, to get the power that eventually goes into the road sign, which was 0.03375. So working backwards, we have to divide by 0.04 to get the solar power that we originally received. And if you do that, then you end up with 0.84375 watts. Okay, the final step is to use the second equation for the solar intensity using the values that we've now worked out and been provided with in the question. If we do that, then we can write that the solar intensity is given by the solar power, so 0.84375, divided by the area they've supplied us with, which is 32 centimeters squared. But since the answer wants us to write it in watts per meter squared, we need to convert the units. So to do that, we need to multiply by 10 to the minus 2 to convert centimeters to meters for each power of centimeters that is in the unit. Now this is centimeters squared, so I have to multiply by 10 to the minus 2 twice, or 10 to the minus 2 squared, which would be 10 to the minus 4. And finally, if I do that, then I get the answer 263.6718 ... which is approximately 260 watts per meter squared, to two significant figures, which is the degree of precision of the data given in the question. So we got 1 mark for calculating the power dissipated in the road sign, we got a second mark for calculating the solar power that we received, and our final mark was for calculating the solar intensity correctly, giving us our final answer of 260 watts per meter squared. This question is about moments in equilibrium. The question says, Figure 7 shows 2 of the forces acting on a uniform ladder resting against a vertical wall. The ladder is at an angle of 60 degrees to the ground. That's what's shown in Figure 7. So the 2 forces that they've drawn are the weight and the resultant force of the wall on the ladder. The question then wants us to explain how Figure 7 shows that the friction between the ladder and the wall is negligible. So when an object rests against another object, there are 2 kinds of forces that can arise as a result of them being in contact. We'll consider a simple example of a box on a plane to illustrate this. The 2 forces that the surface could exact on the block are a normal reaction force, often labelled R, which will stop the block from sinking into the ground. And then there can also be a frictional force, which I'll call F in this case. Now, the normal reaction force, like in the name, normal, is always at 90 degrees to the surface itself. The frictional force, however, will always oppose the motion of the object along the surface, and so will always be at right angles to the surface. As the object is resting on the plane, or the surface, the normal reaction must always be present, but the frictional force doesn't always have to be present. If the frictional force is present, then the resultant force from the object will come off at some kind of angle like this. If there is no frictional force present, then the resultant force is the normal reaction force, and in this case, what we have is just an upward force. We can apply the same principle to understanding the resultant force of the wall on the ladder. The resultant force is at right angles from the wall, and therefore we only see the normal reaction force. The frictional force, if it exists, is too small and does not contribute significantly to the resultant force of the wall on the ladder. Therefore, to get the mark, we need to say that the resultant force of the wall acting on the ladder is at 90 degrees to the wall. The next part of the question says, the forces acting on the ladder are in equilibrium. Draw an arrow on figure 7 to show the direction of the resultant force from the ground acting on the ladder, and label that arrow G. In this question, the important point is that the ladder is in equilibrium. That means that the sum of all the forces acting upon the ladder are 0. Since forces are vectors, we need to add them taking into account their direction. One way to do this is to treat them like arrows, where the length of the arrow represents the size of the force and the direction of the arrow represents the direction of the force. If we do that for the two forces that we already have on the diagram, the force from the wall and the force from the weight, which should be straight downwards, and which I'll label W, then we can see that we're missing a third force, because if the resultant force acting on the ladder is 0, then whenever I add up all these arrows, I should end in the same place that I started. Otherwise, there is a resultant arrow which describes the fact that there would be a force acting on the ladder. Therefore, what we can say is that the missing force, which comes from the ground, has to be in this direction and have that magnitude. So our first mark in this question is for drawing an arrow either upright or to the right. Our second mark is for getting the direction roughly correct. So in order to get the direction roughly correct, we actually need something which will come up in the next part of the question as well. The ladder is also in rotational equilibrium, i.e., it's not rotating clockwise or anti-clockwise. So what that means, then, is that the sum of all the moments acting upon the ladder about any point must be equal to 0. So, without actually doing the calculation, we can imagine taking moments about this point on the ground. So, the moment that comes from the weight will act about halfway up the ladder, since it is a uniform ladder and it has the same density, so the center of mass is in the center. And the resultant force of the wall on the ladder acts at the end of the ladder. These forces, using some geometry, are both at 60 degrees to the axis of the ladder. To see that, we can draw a right-angled triangle here. In other words, here's a right angle. The sum of the angles in a triangle are 180 degrees, so this angle here is 30 degrees. So this angle here is 60 degrees. As for the force from the wall, what we can do is we can use the fact that these are alternate angles. So this is a 60-degree angle, and this is the Z shape that comes with an alternate angle. So this angle here is also 60 degrees. Because of that, we see that the moment from the resultant force of the wall on the ladder is going to have to be equal to the moment from the weight, which implies that the resultant force of the wall on the ladder is less than the force that comes from the weight, because the distance from the pivot point, the ground, to the end of the ladder is greater than the distance from the pivot point to the weight. We've slightly waved our hands when we've given this explanation, because the moment that comes from the resultant force of the wall on the ladder would actually be the value of that force multiplied by sine of 60 degrees to get the component that's perpendicular to the ladder times by the length of times by the distance from the pivot, whereas the weight, the moment that comes from the weight, would be the value of the weight multiplied by cosine of 60 degrees multiplied by the distance from the pivot to the weight. Luckily, because sine of 60 is still greater than cosine of 60, this doesn't affect our conclusion. We will see this explicitly in the next part of the question. Therefore, in the right-angled triangle we've drawn, the weight is going to be the side corresponding to the weight is going to be longer than the side corresponding to the wall, so this line is going to be steeper than 45 degrees. Therefore, if we draw our arrow G, it should look something like this. Here we gain our second mark for getting the angle of G roughly correct, in this case steeper than the angle of the ladder. The next part of the question says, the ladder is 8.0 meters long and weighs 390 newtons. Calculate the magnitude of the resultant force from the wall on the ladder. So, in these kind of questions, it's always helpful to draw yourself a diagram, which we'll do below. So, first I'll draw the ground and the wall, and then we include the ladder, like so. So, the weight acts about halfway and looks like this. And as we said earlier in the question, it's at an angle of 60 degrees to the ladder, like so. Then, if we consider the force from the wall, we also know that this is at 60 degrees from the ladder. Oh my god, my explanation was wrong. So I'm going to call the resultant force from the wall on the ladder, F. Okay, so the third force we need to add is the force from the ground acting upon the ladder, which we call G. So the question wants us to calculate what the value of F is, the magnitude of the resultant force from the wall on the ladder. Now, this question could potentially take a long time because we don't know what G is, so we have to solve for both F and G. However, there is a shortcut we can take. This comes from the fact that if I choose a point to take moments about, then I don't have to consider the moments from any forces that act through that point. This is because the definition of the moment is equal to the force multiplied by the distance from the pivot point to the perpendicular distance from the pivot point to the line of action of the force. What that means then is that because that distance is 0, there is no moment. So we are going to take moments about the point of contact with the ground. Next, we're going to use the fact that the ladder is not rotating. In other words, it's in equilibrium, so it's just sitting there. What that means is that the sum of all moments that want to rotate this ladder anti-clockwise is equal to the sum of all moments that want to rotate this ladder clockwise, because it's not rotating. We know this because the ladder is in equilibrium, like said earlier in the question. So if we take moments then about the point of contact with the ground, then we can use the formula for the moment, which is just the component of the force perpendicular to the object multiplied by the distance from the pivot in each case. So anti-clockwise, we have the force that comes from the resultant force from the wall on the ladder, and so that's at an angle of 60 degrees to the ladder. So we have that the moment is F times by the length of the ladder, which is 8, multiplied by sine of 60 degrees. Okay, as for clockwise, we know that our moment is from the weight, and the distance from the pivot point to the weight is 4 meters. It's half the length of the ladder. So the length of the ladder was 8 meters. So this means that the moment that we get is the weight, which is 390. So W is 390, sorry, multiplied by the distance 4. And then we only want the component of the weight that is acting to rotate the ladder. So this is the component that's going perpendicular to the ladder. The component that goes parallel to the ladder just wants to push it towards the ground. So in this way, we're only looking at the component that rotates it. So to do that, we resolve the force, the weight, along the line that's perpendicular to the ladder. So that means that we need the component that is W multiplied by cosine of 60 degrees. So this is W times 4 times cos of 60 degrees. As a result, we now have our two moments. Now, as we said earlier, the sum of all the moments has to be equal to 0. Or in other words, the anti-clockwise moments have to be equal to the clockwise moments. So we have 8 times F times sine of 60 degrees is equal to W, which I'll substitute for 390, multiplied by 4, multiplied by cosine of 60 degrees. So to get the final answer, F, we divide both sides by 8 multiplied by sine of 60 degrees. So that's 4 times 390 multiplied by cosine of 60 degrees divided by 8 times sine 60 degrees, like so. Calculating that value, what we find, F is equal to 112.583 ... newtons, which, rounding to 3 significant figures, gives you 113 newtons. Note that our expectation that the resultant force from the wall acting on the ladder was less than the weight was true here, which confirms our logic from before. In this question, we got 1 mark for evaluating either of the moments correctly, 390 times 4 times cosine of 60, for example, and we get the second mark for a correct numerical answer at the end. The final part of the question says, suggest the changes to the forces acting on the ladder that occur when someone climbs the ladder. The final part of the question says, suggest the changes to the forces acting on the ladder that occur when someone climbs the ladder. So, what changes about the diagram that we drew before whenever a person climbs the ladder is that the weight of the ladder plus the person is larger than the weight of just the ladder. So as a result, the first thing we can say is that the normal force from the ground now increases, and this is to balance the vertical force. Secondly, because the normal force from the ground increases to balance the vertical force, it means that the friction from the ground must also increase because the friction is related to the normal force. As a result, the force from the wall must now also increase because this is horizontal, and if there is a greater frictional force to the right, then there must be a greater force from the wall and the ladder to the left to balance this force and keep the ladder in equilibrium. So note that to do all of this, we had to assume that the ladder was in an equilibrium as the person climbs up it. Note that we got 1 mark for saying that the normal force from the ground increases, we got 1 mark for saying that the friction from the ground increases, and we got 1 mark for saying that the force from the wall on the ladder increases as well. This question is about forces, acceleration, and motion of objects that have constant acceleration. The question says, Figure 8 shows a model of a system being designed to move concrete building blocks from an upper to a lower level. And then they show us Figure 8, which has trolley B lower than trolley A, trolley B is empty, and trolley A has blocks on it. And A is presumably moving down, and B is moving up. The question goes on to say, the model consists of two identical trolleys of mass m on a ramp which is at 35 degrees to the horizontal. The trolleys are connected by a wire that passes around a pulley of negligible mass at the top of the ramp. Two concrete blocks, each of mass m, two of them, are loaded onto a trolley A at the top of the ramp. The trolley is released and accelerates to the bottom of the ramp, where it is stopped by a flexible buffer. The blocks are unloaded from trolley A, and two blocks are loaded onto trolley B that is now at the top of the ramp. The trolleys are released, and the process is repeated. Figure 9 shows the side view of a trolley A when it is moving down the ramp. So this is the trolley that has been loaded, and it's moving down because the purpose of the system is to move the blocks from the top to the bottom. The tension in the wire when the trolleys are moving is T. The question wants us to draw and label arrows on Figure 9 to represent the magnitudes and directions of any forces and components of forces that act on trolley A parallel to the ramp as it travels down the ramp. So to do this question, we consider all the forces that are acting on the trolley and then work our way down to only the ones that have a component acting parallel to the ramp. So to do that, we will draw a second diagram demonstrating all the forces on the trolley, so as not to mess up the original diagram we need to label. So here's our simple diagram. Now, in this case, here's our diagram. So the forces acting on the trolley consist of firstly the weight of the trolley plus the blocks, which is just given by that total mass of the trolley plus the blocks multiplied by the acceleration due to gravity, g. So that's using the equation W. The weight of an object is equal to the mass times by g. And I've written mass there because we've already got big M and little m as part of our problem. So we can write that down, and that will be going straight down because it wants to pull the trolley towards the earth. And so that force is given by big M, the mass of the trolley, plus 2 times little m, the mass of the blocks, multiplied by g. Okay, the other forces we have then are a normal reaction force from the surface of the ramp, and that will be going perpendicular to the ramp. The normal reaction itself is always at 90 degrees to the surface. If there was friction too, this would act down the ramp. We're told later in the question that we don't need to consider friction here. Finally, the other force comes from the tension in the string, and that's pulling the trolley up the ramp, like so. And that's T. So in each case, we need to resolve the forces involved into two components, the component parallel to the ramp and the component perpendicular to the ramp. So in the case of the normal reaction force, there is only a component perpendicular to the ramp because it points directly out of the ramp. As for the tension, there is only a component parallel to the ramp because it is already pointing only up the ramp and not at some angle. The more difficult force is the weight, which is at some angle to the ramp rather than pointing directly into the ramp or directly parallel to the surface of the ramp. So in order to do that, we can use the fact that this is a right-angled triangle and the angles in a triangle add up to 180 degrees. That means that 90 plus 35 is 125, so the remaining angle in this triangle would be 65 degrees. Then we use the fact that the ramp and the normal to the ramp make a right angle, so this angle here, this 65 degrees, has to add up with whatever remaining angle there is to give you 90. Therefore, this angle, this other angle, is 35 degrees. So at this point, we can resolve forces. We can resolve the weight into its components perpendicular and parallel to the ramp. And we're only interested in its component parallel to the ramp. So to do that, we need to multiply by the sine of 35 degrees, because that will give us the component parallel to the ramp. We can see this by drawing a triangle that shows the two axes that we resolve along. So specifically, parallel to the slope and perpendicular to the slope. And the weight looks like this. And so the angle here is 35 degrees. So we can see that if the weight has size m plus 2m times g, we can get the size of that by doing the size of the parallel component to the slope by doing m plus 2m times g times by sine 35 degrees. And that will get you the size of this arrow here, the arrow going parallel to the slope. So, drawing these forces then on the diagram, we have the tension going upwards, which we label T, and we also have the force coming downwards from the weight, like so. And we label that as big M plus 2 times little m times by g times by sine 35 degrees. And that will get us our mark. The question then says, assume that no friction acts at the axle of the pulley or at the axles of the trolleys, and that air resistance is negligible. What this means is that the only forces acting parallel to the slope on the trolleys are the tension in the string and the weights of the trolleys. The question then wants us to show that the acceleration of trolley B along the ramp is given by A is equal to little m times g times sine of 35 degrees divided by big M plus little m. To do this question, we will need two key facts. Firstly, we will need that the acceleration of both trolleys is the same. So the acceleration A of trolley B is the same as the acceleration A of trolley A. Secondly, we'll need that the tension in the string is the same for both of the trolleys. The reason that this is true is because we take the string to not extend, and because the string does not extend, the trolley A is connected directly to the trolley B. What this means then is that if A accelerates by a certain amount, B must also accelerate by a certain amount to keep the distance between them the same, which is what we mean when we say that the string does not extend. Because the string does not extend, it also makes the tension the same everywhere in the string. At this point, we can reuse our diagram for the trolley A, which looked like this. So we had the trolley on the ramp with the two blocks. So the trolley had mass big M and the blocks of mass little m, and there were two of them. And we said that there was the tension trying to pull trolley A up, and then the weight pulling trolley A down. And so this weight was given by big M plus 2 times little m times g times sine 35 degrees. Then we could draw a similar diagram for trolley B. So B is being pulled upwards, but the forces on it look very similar. So there is still a tension pulling B upwards. B is unloaded, so there's no blocks like I've drawn over here. And then pulling it downwards is just its weight resolved parallel to the slope in the same way that we did for trolley A. So these are the forces acting on B. We've just taken the component of its weight, which is big M times G, parallel to the ramp, which gives us the sine of 35 degrees like I explained earlier. Now we can write two equations that describe the acceleration of A and the acceleration of B. To do this, we use Newton's second law for an object where the mass is constant. So in other words, Newton's second law says that the resultant force acting on an object is given by the rate of change of its momentum, delta p, divided by delta t, which whenever the mass of the object in question is constant, we end up with the mass times by its acceleration. Okay, so for A then, since A is going downwards, the acceleration is downwards, so that means that the weight plus 2m times g times sine 35 minus the tension is going to be equal to the mass of A, big M plus 2 times little m, times by its acceleration, A. We can then do the same thing for B, where we say that the tension minus the weight, because B is accelerating upwards and both A and B have the same value of the acceleration. So T minus mg sine 35, the component of the weight going down the slope, is equal to big M times by A. At this point, what we need to do is add these two equations together. The reason that we want to add the two equations together is because the question has asked us to find the acceleration of trolley B, which is, in other words, the acceleration of both trolleys. In other words, we're trying to solve a set of two simultaneous equations to find the value of A. But the quickest way to get rid of the other unknown variable, which is t, is to add these equations together. Because when I do that, I will get t minus t, which is equal to 0, and have only an equation left containing A. So if we do that then we can write m, big M, plus 2m g sine of 35 degrees minus t, so that's the first part from A, plus t minus mg sine of 35 degrees is equal to big M plus 2m times A plus big M times A. So as I said, the t's cancel, and if I tidy up these terms, then I'm left with this m g sine 35 degrees cancels with the other big M times g times sine of 35 degrees, leaving me with 2mg sine 35 degrees. And then on this side, on the other side, I collect these terms together, so I'm left with 2 times big M plus 2 times little m, all times by A. So I pull the factor of 2 out to get 2 big M plus little m times A. Then I divide both sides by 2 multiplied by big M plus little m, and that leaves me with the final answer. A is equal to little m rather, g sine of 35 degrees divided by big M plus little m. So in this question, we got 1 mark for writing down equations that relate the forces on the trolley A and the trolley B to their accelerations, so these two equations here. And we got 1 mark for adding these equations together and then getting the final answer for A. So the next part of the question says, compare the momentum of loaded trolley A as it moves downwards with the momentum of loaded trolley B. To do this question, it is important to realize that loaded trolley A is exactly the same as loaded trolley B, because in each case, both of them have the same mass, both of them are loaded with 2 blocks which also each have the same mass, and both of them are moving downwards. Thus, because both trolleys have the same mass, they experience the same acceleration and therefore have the same momentum. This is true because the definition of momentum, P, is equal to the mass of an object times by its velocity. Now, if we compare the two trolleys at one point during their travel from the top of the slope to the bottom, then because they have the same mass and experience the same acceleration, what it means is that at that point, their velocities will be the same. They'll both be downwards and they'll both have the same magnitude. Therefore, their momenta also have to be the same. You can apply this to any point as each trolley travels from the top of the slope to the bottom. In this question, we got the first mark for saying that both trolleys have the same mass or the same acceleration, and the second mark for saying that they have the same momentum. The next part of the question says, in practice, for safety reasons, there is a friction brake in the pulley that provides a resistive force to reduce the acceleration to 25% of the maximum possible acceleration. The distance traveled for each journey down the ramp is 9.0 meters. They then tell us that the mass of a trolley big M is 95 kilograms and the mass of a concrete block little m is about 30 kilograms. And they want us to calculate the time taken for a loaded trolley to travel down the ramp. So, taking stock of what we have so far, we know that the acceleration of a loaded trolley, as worked out earlier in a different subpart of the question, was little m times g times sine of 35 degrees divided by big M plus little m. Now this was the maximum possible acceleration, so we're told that there is a friction brake which produces a resistive force to reduce the acceleration to 25% of its maximum value. This then gives that the actual acceleration is a quarter of this. So in other words, it's equal to 0.25 times by little m times g times sine of 35 degrees divided by big M plus little m. Substituting in the numbers, this is 0.25 times by 30 times 9.81 times sine of 35 degrees divided by 95 plus 30. And that gives us 0.3376 ... which we won't round because it's an intermediate value. So at this point, we need to find a way to calculate the time taken for the trolley to travel down the ramp. So we want the time, and what we've been given is the distance, s, and we also have the acceleration, a. Or rather, I'll call this a prime to avoid confusing it with the value of a for the maximum acceleration found earlier in the question. We also know that the initial velocity of a trolley has to be equal to 0, since it is held at the top and then released. So what we are looking for is a Suvat equation, an equation of constant acceleration, which contains t, s, a, and u. The equation that we are interested in then is s, the displacement, or in this case the displacement is the same as the distance, is equal to u times t plus a half times a prime times t squared. So I have replaced the a that you would see if you wrote this equation, if you got this equation from the formula sheet, with a prime to avoid confusing it with the acceleration given earlier in the question. So doing that then, we can rearrange this equation to give us what t must be equal to. So we insert that u is equal to 0, so we don't have to deal with that term again. So this goes away, and we have S is equal to 1/2 times A prime times t squared. We multiply both sides by 2 and divide both sides by A prime. So 2s divided by A prime is equal to t squared. Then we square root both sides to give us t on its own, which is equal to 2s divided by A prime. Finally, we put the values that we've been given in the question into this expression. Namely, t must be equal to 2 multiplied by 9.0, or 9, and divided by the value that we worked out for A prime earlier in the question, which is 0.3376 ... and which we don't round until we get to the final answer. And that gives us an answer of 7.3018 ... which is 7.3 seconds to two significant figures, which is the same degree of precision as given for the values in the question. In this question, we got our marks firstly for calculating the actual acceleration by dividing by 4. We got our second mark for applying s is 1/2 A prime t squared and rearranging it. And we got our third mark for putting the numbers in and getting time is 7.3 seconds. So the time taken to move 2 blocks is just given by 12 seconds, the time taken to unload the blocks from the lower trolley and reload the upper trolley, plus the time taken for the blocks to move from the top to the bottom on the loaded trolley, which is 7.3 seconds, roughly. So that gets us 19.3 seconds. So that's how much time it takes to move 2 blocks. We know that we have 30 minutes. So in this case, we need the total time that we have and divide it by the time taken to transfer 2 blocks. And that will tell us how many blocks we can transfer. So if I have, the total time is 30 minutes times by 60 to turn it into seconds, and that will get you 1,800 seconds. So therefore, total number of blocks is given by 1,800, the total time we have, divided by the time to transfer 2 blocks, multiplied by 2, because we transfer 2 blocks for every journey. So 1,800 divided by 19.3 gives you the number of journeys that's possible to do, and then multiplying by 2 gives you the number of blocks that you've transferred. And if you do that, then you get 186.511. But because you can't transfer more than 186 blocks without transferring 187 blocks, this means that we've transferred 186 blocks. So our final answer is 186 blocks. In this question, we get 1 mark for calculating the total number of journeys, 1,800 divided by 19.3, and we get 1 mark for multiplying that by 2 to get the number of blocks, which here gave us 186. This question is about harmonic motion. The question says, a student is investigating forced vertical oscillations in springs. 2 springs, A and B, are suspended from a horizontal metal rod that is attached to a vibration generator. The stiffness of A is K, and the stiffness of B is 3K. 2 equal masses are suspended from the springs as shown in figure 10. And figure 10 just describes what we've just seen. So we have A and B, which will have spring constants of K, 3K respectively, and both of these masses are just the same. The next part of the question says, the vibration generator is connected to a signal generator. The signal generator is used to vary the frequency of vibration of the metal rod. So what this is saying is that we have forced oscillations because we're choosing the frequency that the masses and the springs vibrate at. When the signal generator is set at 2.0 Hz, the mass attached to spring A oscillates with a maximum amplitude of 2.5 times 10 to the minus 2 meters and has a maximum kinetic energy of 54 millijoules. The question then says, deduce the spring constant K for spring A and the mass m suspended from it. In order to answer this question, since we've been told about the amplitude and the maximum kinetic energy, it is useful to consider the energy transfers going on. So, as A oscillates, it goes for a number of different states. Specifically, when it is furthest away from the equilibrium position at the amplitude, all it has is potential energy. Then, as it returns towards the equilibrium position, that potential energy, which in this case comes from elastic potential from the spring primarily, is converted into kinetic energy. So whenever we're at the equilibrium position, or the mass is at the equilibrium position, then we're only left with kinetic energy. So at the equilibrium position, we have kinetic energy only. If we ignore air resistance, what that means is that the only two forms that the energy can be in are the potential energy and the kinetic energy. And so if we know that we have a maximum kinetic energy of 54 millijoules, and we also know that at the amplitude, the mass isn't moving, because at the amplitude, it's as far away as it's going to be and will subsequently return towards the equilibrium position. Therefore, the velocity of the mass, and thus its kinetic energy, is zero. What that means is that all of that maximum kinetic energy of 54 millijoules is converted into potential energy. So, firstly, in order to get the spring constant then, we can now say something about how the maximum kinetic energy, a value we've been given in the question, is related to the potential energy. To get further, we need an equation that relates the potential energy to the amplitude. We can do that by noting that the potential energy stored in the spring, whenever it stretches by a distance delta L, is given by the potential energy EP is equal to a half times the spring constant times by delta L all squared. So doing this, we can use conservation of energy to say that EP is equal to 54 millijoules, i.e. the maximum kinetic energy that the mass had at the equilibrium position is equal to all the potential energy it has as a result of moving to the amplitude from the equilibrium position. So conservation of energy says that 54 millijoules, the kinetic energy at the equilibrium position, is equal to the potential energy stored in the spring as a result of moving to the amplitude. So that's a half times K times by A squared. So A is the amplitude, and so I'll just replace that by the actual value then of 2.5 times 10 to the minus 2 all squared. And so at this point, to get K, we need to rearrange. So we multiply both sides by 2 and divide both sides by 2.5 times 10 to the minus 2 all squared. So we're left with K is equal to 2 times 54 times 10 to the minus 3, because I've converted millijoules to joules, so that we have the same units of energy on both sides. And then we have that we should divide by 2.5 times 10 to the minus 2 all squared. And when we do that, we get a value of 170 newtons per meter. Now, to get the mass, we need to relate other information that we have in the question to what we already have. And specifically, what we have in the question is the frequency that the mass is vibrating at. We have its amplitude, and we have the maximum kinetic energy, and now we've also worked out the spring constant. So the unused piece of information here is the frequency. So our equation that relates the frequency to the mass and the spring constant is given by F is equal to 1 over 2 pi, multiplied by the square root of k over m. So in order to get the mass, we can use our value of k, which if we rearrange this equation, we can obtain 2 pi times f is equal to the square root of k divided by m. We square both sides, so 2 pi f all squared is equal to k divided by m. So finally, m is equal to k divided by 2 pi f squared. And so in order to do this calculation, we need to use our unrounded answer for k, which I include here as 172.8. And so we substitute that in as 172.8 divided by 2 pi times by f, which is just 2 hertz as given in the question. And that gives us a value of 1.094267 and so on. So what this means then, that our final answer to two significant figures, which is the precision of the data given in the question, is that k is 170 newtons per meter and the mass is 1.1 kilograms. In this question, we got 1 mark for identifying conservation of energy and relating that to k, like so. And we got our 2nd mark for our value of k. We got our 3rd mark for rearranging the frequency formula appropriately to relate the mass to the spring constant. And we got our 4th mark for actually calculating that mass. The next part of the question says, calculate the frequency at which the mass attached to spring B oscillates with maximum amplitude. So, in order to answer this question, we need a few facts. Firstly, we need that the frequency of oscillations at which you have the maximum amplitude is the natural frequency for the system that you are dealing with. This natural frequency is given by the equation f is equal to 1 divided by 2 pi multiplied by the square root of the spring constant divided by the mass of the thing that's oscillating. Note that this is related to the equation given on the formula sheet by the expression f is equal to 1 over t. So f is the frequency of oscillations, and this is just the reciprocal of the time period of oscillations. So if I have a certain number of oscillations per second, then that means that if I divide that second by the number of oscillations, I get the time taken to do one oscillation. And that's related to the equation given on the formula sheet. T is equal to 2 pi times by the square root of the mass of the oscillating thing divided by the spring constant of the spring attached to the mass. It would be sufficient to quote the frequency equation, however. So, from this equation then, we need to identify what the spring constant for spring B is, and we need to identify what the mass is. So to do that, we return to further up, where we see that the other key piece of information we need is that the masses are equal. So for this, we can reuse our value of the mass, 1.1, or we should really use our unrounded answer, 1.0942, etc. For the mass. We're also told that spring B has a stiffness of 3K, where K was the stiffness of spring A. So in order to work out the frequency then, we can also reuse our value of k from the first part of the question, like so. Therefore, what we can find then is that we can substitute the appropriate values into the equation like so. The frequency, f, is given by 1 over 2 pi multiplied by the square root of 3 times the full value of the spring constant, because we shouldn't round in an intermediate calculation. So that's 172.8 divided by the value of the mass, which is the same as we had before. So that's 1.0942687. So 1.0942687 ... And so this gives us a final frequency of 3.46 ... which to two significant figures, which is the degree of precision of the data given in the question, is 3.5. So our final answer is 3.5 Hertz. Note that we got 1 mark here for correct use of the frequency formula and 1 mark for our final answer. Note that there is also another way to do this question, specifically to note that because f is proportional to the square root of k, the spring constant, then we could have just multiplied 2 by the square root of 3 to get the new value of the frequency, because the spring constant for B has increased by a factor of 3, the mass is the same, so we just have f, the new frequency, is equal to square root of 3 times by the old frequency. However, you could have done either way and still gotten the marks. The next part of the question says, figure 11 shows how the amplitude of the oscillations of the mass varies with the frequency for spring A. So the amplitude is what we're interested in here. So what we see is a graph which increases to a peak before coming back down towards 0 as the frequency increases. The question says, the investigation is repeated with the mass attached to spring B immersed in a beaker of oil. A graph of the variation of amplitude with frequency for spring B is different for the graph in figure 11. The question then says, explain 2 differences in the graph for spring B. So in this question, 2 things are happening. Firstly, we've changed from A to B. And we've also immersed in oil. The effects of these are respectively higher natural frequency, like we calculated in the previous part of the question, and also that there is more drag. So there is more resistance to the motion of the mass because it is moving through a thicker fluid, a more viscous fluid, and therefore it is harder for the mass to oscillate back and forth. Now, using what we know about this graph, we see the maximum amplitude, as stated earlier in the question, when the mass oscillates at its natural frequency. Now, in this case, because we've gone from mass A, or from spring A to spring B, we know that the natural frequency is higher for B, because that is what we calculated in the previous part of the question. Therefore, we can get 1 mark straight away for saying that the peak should be at a higher frequency, this higher frequency being about 3.5 Hertz. So our first mark is for saying the peak is at a higher frequency. And this is because B has a larger spring constant. The second part of our answer is going to come from describing the effect of immersing the mass in oil, which has led to more drag, as we said. The effect of this drag is that some of the kinetic energy of the mass is going to be lost as it moves due to collisions with particles in the fluid, in this case the oil. What this means then is that some of the energy is lost. From earlier in the question, we said that the maximum kinetic energy was completely converted into the potential energy stored in the string. However, in this case, some of that energy is lost each time the mass moves through a single oscillation. Specifically, I go from my equilibrium position to my amplitude, and as I do so, I lose some energy to drag. What that means then is that I can get to a less high amplitude because the amplitude is related to the potential energy stored in the spring. Therefore, as a result, I have lower amplitude oscillations. So therefore, the peak and in fact the entire curve will be lower than for spring A. So in this question, we got 1 mark for saying that the peak is at a higher natural frequency, and another mark for explaining why that is true, because of the larger spring constant of B. We got our 3rd mark for saying the effect that the amplitude is lower at all frequencies, and we get our 4th mark for saying that that's due to energy losses. You don't explicitly need to say that that's due to the mass moving through viscous oil, though. This question is about specific charge. The question says, an atom of 16,7 nitrogen gains 3 electrons. What is the specific charge of the ion? So to do this question, we need the definition of specific charge. The definition of specific charge is the amount of charge of the object divided by its mass. In this case, the mass of the ion. So we need to calculate those two quantities. Firstly, the amount of charge that's on the ion is just given by the charge of the 3 negative electrons. To see this, we need to use the fact that an atom is overall neutral, i.e. the nitrogen atom itself here is neutral, so the only charge that we've got is the charge from the 3 electrons. Okay, now as for the mass, we can calculate the mass by taking the number of protons in the nitrogen nucleus and multiplying that by the mass of a proton, and then adding that to the number of neutrons in the nitrogen nucleus and multiplying that by the mass of a neutron. So the atomic number gives you the number of protons. So that's 7 multiplied by MP, which is the proton mass. So that's the mass of the protons in the nucleus. And then I can also calculate the number of neutrons by taking the mass number, 16, and subtracting the number of protons off, which will just give me the number of neutrons. So remember that the mass number describes the number of nucleons in the nucleus altogether. So 16 minus 7 gives us the number of neutrons. I then multiply that by Mn, which is the neutron mass. So finally, to get the answer then, we need to calculate the specific charge as minus 3. Now this is because the electrons are negative, and there are 3 of them, multiplied by the elementary charge, which is the size of the charge on the electron. And then on the bottom, I have 7 times by the proton mass, which is 1.673 times 10 to the minus 27, plus 16 minus 7, that's 9, times by the neutron mass, which is 1.675 times 10 to the minus 27. And when you do that, you get about minus 1.8 times 10 to the 7 coulombs per kilogram. I.e., if I had 1 kilogram of these nitrogen ions that have gained the 3 electrons, it would have this much charge. As a result, our answer is B. Note here that because the neutron mass is very similar to the proton mass, we're not going to get a significantly different answer if we just say that all the nucleons weigh the same thing. For example, if we said they all weighed the proton mass. However, in order to do the most complete calculation possible, you should separate the mass out into the proton mass and the neutron mass. This question is about particle physics. The question says, which diagram represents the process of beta plus decay? So, to answer this question, we need to use our knowledge of what beta plus decay is. So first we will look at it in terms of nucleons, and then we will look at it in terms of quarks, which is what these Feynman diagrams are showing us. So in beta plus decay, we have a process that a proton goes to a neutron plus a positron to conserve charge. So we include all our mass and charge numbers here. Then we have neutron has a mass of 1 and a charge of 0. Positron has a mass of essentially 0 and a charge of +1. And then in order to balance our lepton number, we also have an electron neutrino, because the positron has a lepton number of -1, so we need a lepton of number +1 and charge 0 to keep the charges the same on both sides. Thus the only lepton that can fit the bill is the electron neutrino. Okay, so that's what's going on in terms of proton to neutron. Now we can zoom in and see what happens to the individual quarks. So in a proton, we have the quark composition up, up, down, which gives you an overall charge of +1. And in a neutron, we have the quark composition up, down, down. So in this case, we've gone from an up quark to a down quark. Therefore, what we're looking for is a diagram which shows us an up quark becoming a down quark. As a result, the charge will have to be conserved, and so we expect to see coming out a positron and an electron neutrino. So we can compare the diagrams that we've been given here. So for example, in A, we have an up quark coming in, a down quark coming out. Beta plus decay is a weak decay, so we need either a W or a Z boson here, and that W or Z boson, well, the W bosons, because the Z boson is neutral, the W bosons have to be positively charged to carry the charge that's going to go into the positron, so W plus, and then we need to emit a beta plus particle, which is a positron, and an electron neutrino. So A fits the bill. If we look at some of these other diagrams, then we can see various things that might be wrong with them. So for example, B is no good, because in this case, this is an anti-neutrino. So this would be a good way to rule out this diagram straight away. In part C, we have a down quark going to an up quark, so that's no good, because we've just said that we need to have an up quark going to a down quark. So these two should be switched. So this is no good. And in D, we have a down quark going to an up quark, so that's okay. But we've produced and in D, we have the same problem where we have a down quark going to an up quark. So that's no good. Therefore, the answer to this question is A. This question is about light. The question says, a beam of light of wavelength lambda is incident on a clean metal surface and photoelectrons are emitted. The wavelength of the light is halved, but the energy instant per second is kept the same. And they want us to say which row in the table is correct. So in order to answer this question, it will be helpful to formulate the problem in terms of the wavelength and the number of photons, which are the pieces of information given in the question. So to do that, we can say that the wavelength before is just lambda, the number of photons before is just n, this is number of photons, and these quantities were both for before we make the change in the wavelength. Afterwards, we'll use the symbols lambda n, or lambda nu, which is the new wavelength, and we've been told that that's lambda over 2. And we'll also use the symbol n nu, which is the new number of photons. And by using our constraint that the energy instant per second is kept the same, we're going to figure out what n nu has to be. The reason that n nu is important is because it's going to tell us about the number of photoelectrons emitted per second. More on that later. So the next step is to relate the energy of a photon to its wavelength, because the total energy incident, so energy instant, like so, beforehand was equal to the number of photons times by the energy of a photon. Now, the energy of the photon is given by an equation in terms of the frequency. So E photon is h times the frequency, where h is Planck's constant. This doesn't include the wavelength at this point, so we need to include another equation that relates the frequency to the wavelength. To do so, we use the equation, the wave speed equation, which is that the speed of light is equal to the frequency times by the wavelength. Then, so that we end up with an equation that relates E photon to lambda, we divide both sides of c is f lambda by lambda to make the equation, to make f the subject of this equation, and then we substitute it in. So, in other words, f is c over lambda, so E photon has to be hc over lambda. So the total instant energy then, which I will abbreviate as instant E, is equal to n times hc divided by lambda. Okay, good. So we can now use this equation for both cases, both before the wavelength is halved and afterwards. We know that the total instant energy is the same each time. So what that means is that n times h times c divided by lambda, the instant energy before, is equal to n nu times h times c, which is also a constant, and then divided all by lambda nu. So we know that lambda nu is lambda divided by 2. So what we end up with is that n divided by lambda, divide both sides by h and c to get them out of the equation since they're constant anyway and they appear on both sides, is equal to n nu divided by lambda divided by 2. Okay, so then multiply both sides by lambda to get them out of the equation, and so we find that n nu, the new number of photons, is equal to n divided by 2. So what we see is that the new number of photons incident is equal to half of the old number of photons incident. The last step is to relate this to the actual photoelectrons that are emitted. In the photoelectric effect, the interaction is 1-to-1, i.e., if I have one photon that comes in, one photoelectron will come out, provided that it's got enough energy. So, if I've decreased the number of photoelectrons, or if I decrease the number of photons incident rather, then I must also decrease the number of photoelectrons that come out. Therefore, the only answer that can be correct is C. We can check this by also using conservation of energy. Since each photon has more energy, it has more energy that it can give to an individual electron. And so even though some of that energy is used up escaping the metal, which is given by the work function, overall our photoelectrons should have more energy. Therefore, C is the only answer that fulfills both of these criteria, and we've even checked our work. This question is about wave-particle duality. The question says, electrons moving in a beam have the same de Broglie wavelength or de Broglie wavelength as protons in a separate beam moving at a speed of 2.8 times 10 to the 4 meters per second. And they want us to figure out what the speed of the electrons is. In order to do this question, we need to recall the definition of the de Broglie wavelength, specifically that the de Broglie wavelength, lambda, is equal to Planck's constant divided by the momentum of the particles in the beam. We've been told that the electrons have the same de Broglie wavelength as the protons. Therefore, if I give these subscripts that describe the electron and the proton, i.e. the de Broglie wavelength of the electron, lambda e, is equal to h, Planck's constant, which is a constant, so the same for both the electrons and the protons, divided by their momentum, pe. I can do the same thing for the protons, lambda p is equal to h divided by p subscript p. So then I know that lambda e is equal to lambda p. So I can say that h divided by p subscript e is equal to h divided by p subscript p. So then I divide h from both sides since it's a constant, and then multiply both sides by p subscript p and p subscript e. So I have the equation that p subscript p is equal to p subscript e. Nearly there. So finally, we need to use the equation that relates the momentum of a particle to its speed, because the speed is the quantity that we're interested in, and we've also been given data in the question in terms of speed. So to do this, we use the equation P is equal to m times v, where m is the mass of the object and v is its velocity, which in this case, it'll be the same as using the speed because they're all moving in one direction. And so we don't need to worry too much about the vectors, the vector nature of the velocity. So what we have then is that the mass of the proton, mp, times by the proton speed, vp, is equal to the mass of the electron, me, times by the electron speed, which is the variable we're interested in, ve. Then our final step is to say that ve is equal to the mass of the proton times by the velocity of the protons divided by the mass of the electron. And then we can put the numbers in, 1.673 times 10 to the minus 27, times by the speed given to us, 2.8 times 10 to the 4, divided by the mass of the electron, which is 9.109 times 10 to the minus 31. And if you do that calculation, then you find an answer that's about 5.1 times 10 to the 7 meters per second, which means that our answer is D. Note that we can do a bit of a sanity check here. Specifically, since we're dealing with the electrons, and we know that the momenta have to be the same, the electrons have a much smaller mass, and so to have than the protons, and so to have the same momentum, they must have a much bigger velocity to compensate for it, since the formula is P is equal to mv, and m is smaller, so v must be bigger to keep P the same. This question is about the hydrogen atom, energy levels, and quantum mechanics. The question says, the diagram shows an energy level diagram for a hydrogen atom. Electrons with energy 13.0 electron volts collide with atoms of hydrogen in their ground state. What is the number of different wavelengths of electromagnetic radiation that could be emitted when the atoms de-excite? There are a few different concepts to unpack in doing this question. Firstly, we're told that the electrons collide with atoms of hydrogen in their ground state. So atoms will start with an energy of minus 13.6 electron volts. Then they can absorb up to 13.0 electron volts of energy as they collide with the electrons. So they're going to be excited to some higher level. However, since they can only absorb 13.0 electron volts, what that means is that they don't quite have enough energy to make it to level 4. This is because the difference in the energy levels, so the difference there is 13.06. Therefore, the electrons cannot supply sufficient energy to excite the atom to level 4. However, we can go to level 3 by this logic, because we can we can calculate the difference between them as 13.6 minus 0.85, and that is 12.75. So we can do that. As a result, the atom will get excited to level either 1, 2, or 3, because the energy differences between the ground state and level 1 and the ground state and level 2, the ground state and level 3 are all less than the maximum energy they could get from the electrons. Note that this is not like an interaction with a photon, where a photon is absorbed by the atom and the photon has to have the exact amount of energy to excite the atom from its ground state to a level. In this case, we can get up to 13.0 electron volts from conservation of energy, because the electron can also go on its way and take some energy with it after the collision. So, the maximum number of photons that we can get, which is or the photon energies we can get, which is related to their wavelengths, because we can combine the equations E is equal to hf, which only contains the frequency of the radiation, not the wavelength, and so we need another equation to relate the two, with C is equal to f times lambda, where c is the speed of light, f is the frequency, lambda is the wavelength, and I should say h is Planck's constant, which is a constant. We make f the subject in this second equation, and then what we end up with is an equation which looks like E is equal to h times c. So I substitute in the new equation for f is c over lambda, to get E is equal to hc over lambda. So identifying the different photon energies gives you the different wavelengths that you could get as well. So it's fine to say that the number of different wavelengths is equal to the number of different photon energies. So now we need to identify what those photon energies could be, or at least how many different ones there are. And so in order to do that then, we need to calculate how many different ways I can go from level 3 back to the ground state, or from level 3 to a lower level. And then the same for level 2 and level 1. So I get one photon from going from level 1 to the ground state. I get another photon from going from level 2 to level 1. And I get another photon from going to level 3 from level 2. We have to decay, our atom has to de-excite exactly like this, because it can only take energies that are given by the values of the energy levels. So that's 3 photons. Now, from level 3, I can also go straight from level 3 to level 1, like so. So that's another photon. I can also go straight from level 3 back to the ground state, like so. So that's a 5th photon. And then finally, I could also go from level 2 straight back to the ground state. So that's another photon. And if we count up the number of arrows we've now drawn that represent the different energy differences, and thus the different wavelengths that we would get as these atoms decay, or de-excite rather, what we end up with is 1, 2, 3, 4, 5, 6. So therefore our answer is C. 6 different wavelengths, because we have 6 different photon energies that we could get from this atom de-exciting. This question says, the graph shows how the vertical height of a traveling wave varies with distance along the path of the wave. On the y-axis, we have the vertical height of the wave, and on the horizontal axis, we have the horizontal distance in centimeters. So what we're seeing here is the actual wave profile that you would see at one point in time if you looked at the wave side on. We're told in the question that the speed of the wave is 20 centimeters per second, and they want us to work out the period of the wave. So to do this, what we need to do is relate the wavelength, which is a piece of information that we can obtain for the graph, and which I'll show you shortly, to the period of the wave. So to do that, we use 2 equations. Firstly, we use the wave equation, c is equal to f times by lambda. So c is the speed of the wave, and that's equal to the frequency multiplied by the wavelength. Now, at this point, the question wants us to work out the period, which is the time period. And so this is the reciprocal of the frequency. The intuition behind this equation is that the frequency tells us how many times the wave oscillates every second, or rather, how many peaks pass a point every second. So therefore, if I know that there are a certain number of oscillations every second, if I do 1 divided by the number of oscillations, then that tells me how many seconds it takes to do a single oscillation. So from there, what we can do is we can substitute this equation, f is equal to 1 over t, into this equation, c is equal to f lambda, to get a new equation, which says that c is equal to t, or lambda divided by t. And then we rearrange for t, the time period. So t is equal to lambda divided by c, where c is still the wave speed. Okay, so at this point, we need to read off what the wavelength is on the graph. So to do that, what we're looking for is the distance between 2 points that are in phase on the wave profile. A perfectly good set is the one at the very start, to make life easy, and the next peak. So the distance between these 2 peaks. And so that distance is 4 centimeters. So lambda is equal to 4 centimeters. And I'll just mark that on with an arrow as the wavelength. Okay, from there, what we can do is we can say that we can use our equation. Now, normally we would have to convert units to get everything into SI units, but here we can take a bit of a shortcut. So because the wave speed has been given to us in centimeters per second, and the wavelength is also in centimeters, these units are going to cancel. So specifically, if I do t is equal to 4 centimeters divided by 20 centimeters per second, these two are going to cancel, like so. And so we're left with 4 divided by 20 divided per second, which is just seconds. So t is equal to 4 divided by 20, which is 0.2, and then seconds. So we took a shortcut and didn't have to convert the units here. Thus, the answer is B. This question is about waves. The question says, which statement is not correct for ultrasound and X-rays? And our options are A, both can be refracted, B, both can be diffracted, C, both can be polarized, and D, both can be reflected. In order to answer this question, we need to go through the various options and decide which are true for both and which are not. The easiest way to do this question is to observe the differences between the two types of wave. Specifically, ultrasound. What we know is that it is mechanical and longitudinal, i.e., the direction of oscillation is the same as the direction of energy propagation in the wave. On the other hand, we know that X-rays are electromagnetic and they're also transverse. So now what we should do is we should go through our list of properties that we've said, one of which is not correct for both ultrasound and X-rays, and decide which does not apply to these properties that we've listed here. So the first says both can be refracted. Both longitudinal and transverse waves can be refracted, and there's nothing about ultrasound being a mechanical wave versus X-rays being an electromagnetic wave that says this can't be true. This is also true for B and D, because both types of waves can be diffracted and reflected. There's nothing about it being a mechanical wave that says it can't also be diffracted, and longitudinal waves can still be diffracted. Similarly, EM waves can still be diffracted and also reflected, just as ultrasound can. So finally, we're left with C, which says both can be polarized. Now, a transverse wave can be polarized because the idea of polarization is to control the direction of oscillation. A longitudinal wave, on the other hand, cannot be polarized because the direction of oscillation of the particles is along the direction of energy propagation. Therefore, if you were to attempt to stop the particles from oscillating along the direction of propagation, then the wave wouldn't be able to propagate at all. Thus, since ultrasound is a longitudinal wave, it cannot be polarized. However, for X-rays, there are two different independent directions that the particles could oscillate in about the direction of energy propagation. So if the direction of energy propagation is this way, then particles can either oscillate upwards and still be perpendicular, or they can come out of the screen and still oscillate perpendicular to the direction of energy propagation. Any oscillation will be a combination of particles moving in and out of the screen and moving up and down, which added together gives something which in general looks diagonal. So therefore, the polarization is just a way of selecting the direction that these particles oscillate in perpendicular to the direction of energy propagation. Therefore, it's only possible to do this for transverse waves, so our answer would have to be C. This question is about stationary waves. The question says, a stationary wave is set up on a stretched string of length L and diameter d. Another stationary wave is also set up on a second string made from the same material with the same tension as the first. What length and diameter are required for the second string so that both strings have the same first harmonic frequency? Our first step for this question is to recall the equation that describes the first harmonic frequency in terms of the tension in the string and the linear density. In other words, the frequency, F, is equal to 1 divided by 2 times the length of the string multiplied by the square root of the tension divided by the linear density, mu. From here, we need to rephrase this equation in terms of the diameter of the string. From there then, we need to substitute in an equation for mu in terms of the density, which will be the same because they're made of the same material. So in order to do that then, we can write that mu, the linear density, is equal to rho, the actual density, multiplied by A, the area. We've chosen this equation because the area will contain the diameter. We generally take these strings to be cylinders with a circular cross-section. So we can say that the area, the cross-sectional area, remember, is equal to pi multiplied by the radius of the string squared. And the radius is nothing but the diameter divided by 2. So we have that the area is given by pi times by d over 2 all squared. This means that the linear density is just rho times by pi times by d over 2 all squared. We can then substitute this into our equation for F. So, into F. To obtain F is equal to 1 divided by 2L multiplied by t, square root of t rather, divided by rho times by d over 2 all squared. That's all in the square root. So just going down to the bottom where we've got space, we can simplify this equation and tidy it up as F is equal to 1 over 2 times L times by d over 2. So the 2's cancel. And we're left with 1 over LD times by the square root of t over pi times rho. So now we need to identify what's going to allow us to keep the frequency the same whenever we start changing L and D. Firstly, we know that the tension and the density are all the same. However, like we said, the linear density had to change because that depended on the area, and the diameter might change. So what we have then is that 1 over LD, and thus LD, must remain the same for the frequency to remain the same. This is because this part here is constant already. So this implies that L times D is equal to a constant for F constant. Okay, from there then, we can use that and look at these different combinations of 2L and 2D and so on in order to figure out which one satisfies this rule. So in order to do this then, for the original string, we just have LD. For string A, if I change L to 2L and D to 2D, then the new product of the length and the diameter of the string is 4LD, so this is no good. For B, we haven't changed the length, but we have changed the diameter to 2D, so this is now, so the length times the diameter, the new diameter, remember, which is 2D, gives us 2LD, so that's also no good. For C, we have L over 2 times by 2D. In this case, the 2 cancels with the half to leave us with LD, like so. And just as a check, the last one will give us LD divided by 2, which is also wrong. So therefore, the only one which keeps L times D the same before and after the change is C. This means that since L times D is the same, F has to be the same by the argument we just made. Therefore, the answer has to be C to keep the first harmonic frequency the same. This question is about diffraction. The question says, when a monochromatic light source is incident on two slits of the same width, an interference pattern is produced. One slit is then covered with opaque black paper. What is the effect of covering one slit on the resulting interference pattern? So the useful information in the question we've been told is that we have a monochromatic light source, so there's only one wavelength, and it's incident on two slits of the same width, and an interference pattern is produced. So that's the normal double slit experiment. We're then told that we cover one of the slits with opaque black paper, which means that we go from the double slit experiment to the single slit experiment. And then the question wants us to compare the different results that we get from each of these experiments. So for the double slit case, we have something which looks like this. So the arrow indicates the center of the pattern. So we start with maxima, and then we have alternating maxima and minima, so on. And they should be equally spaced. But this is just a rough diagram, so it won't be perfect. As for the single slit then, what we have is the following. Another central maxima, but this time the size of the intensity is decreasing as you get further out. So this is intensity versus position. And the same single slit. And I should just complete the other side. So it's exactly the same on the other side, like so. Okay, and these are at the same height. So, as in the two maxima at the center are at the same height. So keep that in mind. So then, by comparing these two different graphs, what we can see is that the intensity for the single slit is decreasing, becoming increasingly smaller as you go further out from the central maximum. However, for the double slit, the intensity of the maxima remains the same as you move across the pattern from the center until you get further out. Therefore, what we would expect to see is fewer maxima for the single slit case than for the double slit case. Therefore, our answer is C. This question is about diffraction gratings. The question says, when light of wavelength 5.0 times 10⁻⁷ meters is incident normally on a diffraction grating, the fourth order maximum is observed at an angle of 30 degrees. What is the number of lines per millimeter on the diffraction grating? So, in order to do this question, we need to use the diffraction grating equation, namely that n lambda is equal to d sine theta. N here is the order of a maximum observed, lambda is the wavelength of the light normally incident upon the grating, d is equal to the spacing between the lines on the grating, and sine of theta is sine of the angle at which the ray comes off the diffraction grating at for that order of maxima. Note that the question has asked us for the lines per millimeter and not the spacing between the lines, which is d. The two quantities are related as d is equal to 1 over the lines per distance. This is like saying, if I have a certain amount of distance between each line, if I do 1 over that, then I end up with the number of lines that I have in a given distance. For example, if I have 2 lines every meter, then 1 over 2 is 0.5 meters between each line. Okay. So firstly then, in order to get the lines per millimeter on the grating, we'll need to calculate d. From d, calculate the lines per millimeter. So firstly, let's rearrange for d. So d is equal to n lambda divided by sine theta. From the question, we get that that n is equal to 4. We have lambda, and we have that theta is 30 degrees. So we have 4 times 5 times 10 to the minus 7 divided by sine of 30 degrees, which is a half. So for d, that gets us a value of 4 times 10 to the minus 6 meters. So this is the spacing between the lines. If we do 1 over this, then we get the lines per meter as 2.5 times 10 to the 5 per meter. Now I note that this is per meter and not per millimeter, which is what the question has asked for. So in order for us to do this, we need to convert meters to millimeters. In other words, 1 meter is 10 to the 3 millimeters. So 1 per meter is equal to 10 to the minus 3 per millimeter. Sorry, I'll put that down here to avoid clashing with the mark, like so. So in other words, we need to multiply d by 10 to the minus 3. So d is equal to 2.5 times 10 to the 2 per millimeter. Note that the intuition of multiplying by 10 to the minus 3 might make sense. If I have a certain number of lines per meter, then I expect to have significantly less per millimeter since there's a smaller space. In other words then, because we now know that d is 2.5 times 10 to the minus 2 per millimeter, we have that the answer is A. This question is about moments and equilibria. The question says, a light, uniform, rigid bar is pivoted at its center. Forces act on the bar at its ends and in the center. Which diagram shows the bar in equilibrium? To answer this question, we need to know about the two different kinds of equilibrium. First, we have equilibrium of forces, as if that comes from Newton's second law, where the sum of the forces gives 0, thus the resultant force is 0. Therefore, for a body with a fixed mass, there is no acceleration. So in other words, one condition is that the resultant force is 0. And that's from Newton's second law for an object with fixed mass, F is ma. And if F is 0, the resultant force, then A has to be 0. And then we also have rotational equilibrium. This is where the sum of the moments acting on an object is also 0. Therefore, if we can satisfy these two conditions, then the object is truly in equilibrium. So in order to do this one, we need to calculate the resultant force acting on the bar in each case and the sum of the moments acting on the bar in each case. From doing so, what we'll find is that one of them will have a 0 resultant force and a 0 resultant moment by adding the moments. So let's start with A, and we'll start by calculating the resultant force. Now, since the force is a vector quantity, we must take care to include the direction in our calculation. So what we'll say is that upward forces are positive and downward forces are negative. Then we can calculate that the upward force is 4 plus 2, and then we subtract the downward force, which is 2 plus 8. And so this is 4 plus 4 plus 2, that's 10, minus 2 plus 8, that's also 10. So our resultant force is equal to 0 here. Then, for the moments, we need to make sure that we consider where the pivot point is. So we're told in the question that the bar is pivoted at its center, like so. So because the pivot is in the center, we only need to consider forces that do not act through the pivot. So in other words, we can ignore the 8 Newton force and the 4 Newton force. This is because using the definition of the moment equal to the force multiplied by the perpendicular distance from the line of action of the force, we find that since these forces act through the pivot, the perpendicular distance to the line of action of the force is just equal to 0. Therefore, these forces produce 0 moment as they are through the pivot. Now we calculate the moments. So in order to determine what direction the moments are acting in, as in whether they want to make the bar rotate anti-clockwise or clockwise, so we need to calculate the moments coming from the forces on either side of the pivot. So the 2 Newton and the 4 Newton on the left-hand side and the 2 Newton on the right-hand side. And to do this, we need the equation for the moment, which is m, the moment, is equal to the magnitude of the force multiplied by the distance from the force, d, multiplied by sine of theta, where theta is the angle of the force to the bar. So in this case, all our angles are right angles, which is going to give us sine theta is equal to 1 here, because theta is 90 degrees. So from here on out, we won't write sine theta in the equation. So the same here and here. Okay, so let's calculate the moment from the 2 Newton force on the right-hand side. If we do that then what we find is that we have a distance of half the length of the bar. So I'll call the entire length of the bar 2 times L. So the moment then is given by the size of the force, 2, multiplied by the distance from the pivot, which is just L, because we've taken it to be the length of the entire bar to be 2L. The center of the bar is at the pivot point, so we only have half the bar here. In other words, this length is L. Okay, so that's the moment from there. From our other 2 Newton force on the left-hand side, we have exactly the same thing. We're at a distance L from the pivot. We're at 90 degrees to the bar, so theta is 90 degrees, sine theta is 1. And so the moment is just F times d again. So the moment here is 2 times L. As for the 4 Newton force, we can perform the same calculation. The moment is equal to 4, the size of the force, times by the distance from the pivot, which is L, times by sine theta, which is sine of 90 degrees, which is still just 1. So now if we add all moments, then we have to be careful to add moments which are causing things to rotate in the clockwise direction separately to moments that are causing things to rotate in the anti-clockwise direction. What I mean then is that this moment on the right hand side, just the 2 Newton force, is causing a rotation this way, which is anti-clockwise, my 2 Newton force on the left-hand side is also causing a rotation anti-clockwise because it wants to push the bar down and to the right. And then the 4 Newton force is causing a rotation clockwise because it wants to push the bar up and to the right. So therefore, if I add all these together and make sure that I subtract either the anti-clockwise or clockwise moments, depending on which one I choose to be positive, then I can write that if I choose clockwise to be positive, 4L minus 2L from the 2 Newton force, from one of the 2 Newton forces, minus another 2L from the others, gives me 0. Therefore, the resultant moment here is also 0. Therefore, bar A is in equilibrium. Thus, the answer is A. If we were to look at some of the other bars, what we would quickly realize is that either from the resultant force being not 0, or from the resultant moment being not 0, is that none of these other bars are in equilibrium. We were just lucky that A was the first one, so we only had to do the calculation once. However, if you did find that one of those two conditions was automatically 0, then it would allow you to quickly eliminate the other possibilities. This question is about kinematic graphs. The question says, which row gives two features of graphs that provide the same information? To answer this question, it is helpful to recap the different types of graphs and the relations between them. So, for the displacement time graph, if I take the gradient of this graph, this is the rate of change of the displacement, which is the velocity. So I get a velocity time graph. Equally, if I take the area under the velocity time graph, that's like multiplying v times t for each little part of the area, so that the total effect is that I calculate the change in the displacement. Therefore, the area under the velocity time graph gives me the displacement, so I can reproduce the displacement time graph from the velocity time graph by looking at the area. Similarly, the rate of change of the velocity gives me the acceleration, which is the gradient of the velocity time graph, so that gives me at. And then in a similar manner as for the velocity to the displacement, taking the acceleration and multiplying by small time intervals for each little part of the area gives me the full area, which will allow me to calculate the change in the velocity. And thus, by looking at the area of the acceleration time graph, I get the velocity time graph back. So, what this means then is that we're looking for two of these arrows. And if we have two of these arrows in our diagram that represent the same quantity, i.e., for example, we want the gradient of the displacement time graph and the area under the acceleration time graph, those two will both give us the velocity, and that's what we're interested in. So let's look now at A, B, C, and D. Which one has both columns representing the same quantity? So for A, we have the gradient of the displacement time graph, that gives us the velocity. For B, for feature 2, we have the area under a velocity time graph, that gives us the displacement, so A is no good. For B, we have the gradient of a displacement time graph, which is again the velocity. And for feature 2, we have the area under the acceleration time graph. This is also the velocity. Just to rule out the other two, just to be sure that we've picked the correct answer. For C, we have the gradient of a velocity time graph, that's A, from up here. And then for feature 2, we have the area under a displacement time graph, and that's just a quantity that we don't use in physics very much, if at all. And for D, we have the gradient of a velocity time graph, which is again A. And then for feature 2, we have the area under an acceleration time graph, which is V. So both C and D are no good because they don't represent the same quantities. Okay, so that means that our answer is B, and we've proven that this is the only one that could possibly work. This question is about Newton's second law. The question says, a rocket of mass 12,000 kilograms accelerates vertically upwards from the surface of the Earth at 1.4 meters per second squared. What is the thrust of the rocket? So the thrust of the rocket is the force that the rocket outputs in order to try and lift itself off the ground. In order to understand this question then, we can first draw a diagram that represents the forces acting upon the rocket. Specifically, we'll have some unknown force, the thrust, and we also have the weight of the rocket. We're told that the rocket is on the surface of the Earth, so the acceleration due to gravity is g. What that means then is that we can now write down an equation which describes the forces acting on the rocket. Specifically, we can write T minus W, so the thrust minus the weight, is equal to the mass of the rocket multiplied by its acceleration. Now, we now need to use that W is equal to mg, since this is the gravitational force. So we have that T is equal to ma plus mg. So here I've substituted mg in as W and added mg to both sides. T is the thrust. So now we can substitute in our values for m and for a and for g, which is 9.81 meters per second squared. And if we do that, then we find that it's 12,000 the mass. And here I've factored out the mass to make life a bit easier. So I've done this algebraic manipulation. And then we have 1.4 is the actual acceleration of the rocket plus 9.81 from the acceleration due to gravity. So what that gives us then is 134,520 newtons, which is approximately 1.3 times 10 to the 5 newtons, which is the degree of precision given in the question. Therefore, we can say that the answer is C. This question is about projectile motion. The question says, Figure 12 shows the path of a projectile launched from the ground level with a speed of 25 meters per second at an angle of 42 degrees to the horizontal. What is the horizontal distance from the starting point of the projectile when it hits the ground? In order to solve this question, we need to figure out the time taken for the particle to get from its initial starting point to its end point when it hits the ground. To do this, we can use the fact that the time taken for the projectile to go from its starting point to its highest point in the flight is the same as the time taken for it to go from its highest point in the flight back to the ground. So, in other words, this part of the flight and this part of the flight have the same time. In order to work out what that time is, we can select a constant acceleration equation and use that to figure out the time. Specifically, we've been given the initial velocity, so we have u. We have the acceleration because that's just equal to minus g. So it's g because that's the acceleration due to gravity, and it's minus because it's going downwards. We want to figure out t. And we also know that at the very top, the vertical velocity is 0. So in other words, at this point here, we have some horizontal velocity, like that, and then our velocity going upwards is 0. Whereas at the start, by resolving the velocity, we have that the horizontal velocity is 25 cos 42 degrees, and we have that the initial vertical velocity is 25 sine 42 degrees in meters per second. So u in this case is equal to 25 sine 42 degrees. So then, an equation that contains all of u, a, v, or rather, sorry, u up, a, t, and v up is v up is equal to u up minus plus a times t. So then let's rearrange that for t to find t is equal to v up minus u up divided by a, which is just equal to minus 25 sine 42 degrees divided by g, or minus g, minus 9.81. So that gives us t is equal to 1.71, is roughly equal to 1.71 seconds. So then, using that, what we can say is that the total time of flight is 2 times this. So that gives us 3.41 seconds. Now we know how long the flight is, so we can apply the equation speed equals distance over time, because we know the velocity of the projectile in the horizontal direction, and that's not going to change because there's no air resistance or any other horizontal force acting upon the particle. So we have its speed, and we have the time, and we want to work out the distance. So we can use speed as distance over time. In other words, the horizontal velocity is equal to the distance divided by t, the time, or rather 2 times t. And then finally, we can rearrange so that d is equal to 2 times v horizontal times by t, which is just equal to v horizontal, which is 25 times cosine of 42 degrees, multiplied by the time, which we worked out earlier. This is 2t, and this is 3.41, ... And if we do that, then we get d is equal to 63, or is equal to 63.4 meters. Roughly speaking, which is approximately equal to 63 meters, which means that our answer then is 63, or D. This question is about conservation of momentum. The question says, a car of mass 580 kilograms collides with the rear of a stationary van of mass 1,200 kilograms. Following the collision, the van moves with a velocity of 6.20 meters per second, and the car recoils in the opposite direction with a velocity of 1.60 meters per second. What is the initial speed of the car? In order to answer this question, it's helpful to consider diagrams of the car and the van before and after the collision. If I draw a diagram of before, then we have the car moving at some unknown speed, which I'll call u, and the car has a mass of 580 kilograms. So this is the car, labeled C, and then we have the van, V, or the van B, which has a mass of 1,200 kilograms. Afterwards, what we have is the car going back in the direction it came with a velocity of 1.60 meters per second. So 1.60 meters per second, and its mass is still 580 kilograms. And we have the van going forward, so this is C, and the van is going forward now, so B, at 6.20 meters per second, like so. And so its velocity, its mass again is 1,200 kilograms. In order to make progress, we now need to consider conservation of momentum. This says that the momentum before any interaction between bodies is the same as the momentum after that interaction in a closed system. Or in other words, if I add up all the momentum before the collision, then that must be the same as the sum of all the momentum after the collision. Note that in the question, we have been given the masses of the car and the van, as well as relevant velocities. Therefore, momentum is the correct quantity to consider because its definition contains only the masses and the velocities. Note that we cannot compare energies because we have not been told that the collision is elastic, and therefore kinetic energy is not necessarily conserved. So to do this, we will need the definition of momentum, which is that P, the momentum P, is equal to the mass of an object multiplied by its velocity, v, where we must be sure to take into account the fact that velocity is a vector. Okay, so the momentum before the collision is 580 multiplied by u, and we'll take that to be positive, and in doing so, what we're saying is that the velocity, any velocities going to the right are positive, and any velocities going to the left are negative. So this 1.660 meters per second here is going to be negative when we write it down in a moment. So it's 580 times by u, the mass of the car, multiplied by its velocity u, which we don't know yet, added to 1,200 times by 0, because 1,200 is the mass of the van, but it's moving at a velocity of 0 because we know it's stationary. Therefore, that's equal to the momentum after the collision, which is just given by 1,200 times by 6.2, which comes from the velocity, the momentum of the van. So the mass of the van multiplied by its velocity, added to the momentum of the car afterwards. So that's 580, and here we have to be careful because the velocity of the car afterwards is in the opposite direction. So this time it's going to the left, so we have to include a minus sign, times minus 1.6. So now we have an equation for u, and in order to solve it, we just divide both sides by 580. So u is equal to 1,200 times 6.2 minus 580 times 1.6, where I've just pulled out the minus sign, dividing that by 580. So that gives us u, the initial velocity of the car, to be equal to 11.2 meters per second, if you put those numbers into a calculator. Therefore, our answer is B. This question is about velocity time graphs. The question says, which graph best represents the velocity time graph for a ball that is dropped from rest and bounces repeatedly? In order to answer this question, there are several key bits of information that will allow us to eliminate various possibilities here. Firstly, we know that the ball is dropped from rest, which means that the velocity initially has to be 0. Therefore, C is automatically out, because the ball is dropped from rest. Next, we must consider what happens to the velocity of the ball as it bounces. Consider the velocity of the ball just before it bounces and just after. So, if we draw some diagrams to represent this situation, we have one here where it's going quickly before it hits the ground, and one where it has that same velocity but going upwards again. We consider this to be an elastic collision, so the speed of the ball is the same in both cases. So this is before and this is after. Now, in this case, the velocity has actually changed direction, but is of the same magnitude. This is because in the before case, it's going directly downwards, and in the after case, it's going directly upwards. However, since the speed is the same, we expect it to go from something fairly large and positive to something fairly large and negative. Note that in the question, the downward velocity has been taken to be positive, and the upward velocity has been taken to be negative. Also, if we consider the forces acting on the ball, then the only force acting at any given time, apart from when it's bouncing, is the gravitational force, or in other words, the weight of the ball. So W is equal to mg. Note that in the question, the downward velocity has been taken to be positive, and the upward velocity has been taken to be negative. Therefore, if we were to do Suvat equations for this, then the ball's velocity could be described by an equation of the form for before the first bounce as v is equal to gt, where we've used v is equal to u plus at, with a is equal to g and u is equal to 0. So what this means then is we expect the velocity to follow a straight line relationship before the first bounce, and indeed for all subsequent bounces. Therefore, what we see then is that A cannot possibly be correct, and nor can D. A has the velocity slowly increasing and then decreasing again, but always staying above 0, so the ball would always be moving downwards in this case. Therefore, this is no good, because the ball cannot bounce if its velocity is always only going downwards. And in the case of D, you have a somewhat straight line relationship before the acceleration changes, which demonstrates that the forces acting on the ball would need to be changing, so this is no good either. If we just think about the graph of B a bit more, just to make sure that we've got the right answer, what this graph corresponds to is the ball being dropped at 0, 0 before it hits the ground. When it hits the ground, the velocity is reversed, like we expected from up here. And then this graph describes the ball coming back upwards. At this point, it's the highest that it gets after a first bounce, and then it starts coming towards the ground again, since the velocity has changed direction. So it's at the ground here. And this pattern just keeps repeating. So this sudden change in direction is associated with the ball bouncing. Therefore, we have good reason to believe that the only answer that works is B. This question is about material properties. The question says, a sample of wire has a Young modulus E. A second sample of wire, made from an identical material, has 3 times the length and half the diameter of the first sample. What is the Young modulus of the second sample of wire in terms of E? For this question, what we need to do is note that the Young modulus is a property of a material, rather than depending on the dimensions of the material. Therefore, the answer can only be B, because changing the dimensions of the material will not affect the Young modulus. Note that this is a confusing question because the question is leading you to potentially assume that the Young modulus changes, whereas actually it is the extension that changes. So delta L changes, not L0. To see this, we can calculate the extension before and after the change is made. So before, we have that the E, using the definition of E, is equal to sigma divided by epsilon. So the Young modulus is given by the tensile stress divided by the tensile strain. We then use the sigma is equal to the force applied divided by the cross-sectional area of the object, which we take to be circular. So A is equal to pi r squared. Now the radius is equal to half of the diameter. So A is equal to pi times d divided by 2, all squared. Then we have that the strain is given by epsilon is equal to delta L, the extension, divided by L0, the original length. Therefore, E is equal to F divided by A divided by delta L divided by L0. Tidying that up and rearranging for delta L, we find that delta L is equal to F times L0 divided by A times E. So at this point, we can consider the case after as well. If we do that, then what we see is that because we've taken the length to increase by 3, so L0 has become 3 times itself for the new wire, and then we also have that the diameter has gone to itself divided by 2. It's been halved. The impact that this has on the area is that the area goes to itself divided by 4, because the area is proportional to the diameter squared. Therefore, we can make these substitutions into the new delta L, where L0 becomes 3L0 and A becomes itself divided by 4, to find that the new delta L is equal to 12 times F times the original L0 divided by the original area times by the Young modulus, which is the same. Therefore, what we see is that the extension is the key property that changes here, not the Young modulus, which is a property only of the material. This question is about circuits. The question says, in the circuit below, the potential difference across the light-emitting diode is 1.8 volts when it is emitting light. The current in the circuit is 20 milliamps. What is the value of the resistor R? So in this question, we have a cell with some kind of internal resistance. So we've been given the EMF 5 volts and the internal resistance 10 ohms. We have the LDR, which we know has a potential difference across it of 1.8 volts. And we have our resistor, which we don't know anything about at this point, except the current through it. In order to proceed then, we can use the voltage law to say that the total voltage dissipated across the three components, the internal resistance, the LED, and the unknown resistor, has to be equal to 5 volts. This is just another way of expressing energy conservation, in that the charges that come from the cell have to give up all their energy as they go around the circuit once. So from this then, we can use Ohm's law, which is V is equal to IR. So what we'll say is that the voltage dropped across all the components in the circuit is equal to the current in the circuit multiplied by the total resistance, which I will call RT. So total resistance of all components in circuit is RT. So then we can say that 5 volts has to be equal to 20 milliamps multiplied by RT. And we'll have to be careful about the units in a little bit. Now we need to calculate the resistance RT. To do that, we need the resistance of the LDR, and then we'll be left with something in terms of the unknown resistance R. So firstly, to get, so this is for the whole circuit, remember. So firstly, to get the resistance of the LED, then we can apply Ohm's law again, but this time use just the voltage drop across the LED. So we can say that V is equal to I R LED. So R LED is just the resistance of the LED. And what we say then is that V, 1.8 volts, because that's what we're told in the question, is equal to 20 milliamps multiplied by R LED. So the reason we did this was because we had been given both the voltage and the current, the voltage across the LED and the current through it. So therefore it was possible to work out the resistance of the LED, which we're then going to use to put back into the total resistance. So working that out, we can write that R LED is equal to 1.8 divided by 20 milliamps, or 20 times 10 to the minus 3 amps, removing the prefix milli, and that gets you 90 ohms. What that means then is that if we substitute this back into our total equation, we have that RT rather, is equal to 5 volts divided by 20 milliamps, which I will again convert into amps by multiplying by 10 to the minus 3, which removes the prefix milli. And then that has to be equal to the sum of the three resistances. In other words, the total resistance is just R plus the resistance we worked out for the LED, which was 90 ohms, plus the internal resistance, which is 10 ohms. We add the resistances together in this way because this is a series circuit, so the resistances add normally. Therefore, R, the unknown resistance, is equal to 5 divided by 20 times 10 to the minus 3, minus 90 minus 10. And if we do that calculation, then we get that R is equal to 150 ohms. Therefore, our answer is C. This question is about resistors connected in parallel. The question says, the combined resistance of n identical resistors connected in parallel is Rn. Which statement correctly describes the variation of Rn as n increases? In order to do this question, it is helpful to consider the formula for combined resistances in parallel. In other words, my total resistance, RT, if I connect a load of resistors in parallel, where we don't know what they are yet, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... and so on. Okay, so we know that then if we do 1 over this value, we'll get the total resistance. So now let's apply this to our situation. In our situation, R1 is equal to R2 is equal to R3 and so on. And that's equal to R, where we'll just give it some value R, which we don't know. Then what we can say is that 1 over Rn, the total resistance, which has been given to us in the question, is equal to 1 over R plus 1 over R plus ... And we have n times, or n copies of 1 over R. Therefore, what we can say is that 1 over Rn is equal to n times by 1 over R, like so. Then we can invert this, so we take the reciprocal of this equation, so we get that Rn is equal to R divided by n. Therefore, now consider what happens if we increase n. If we take n to be quite a small number, for example 2, and then we start increasing it by making it larger and larger, and say we go to 10,000 or something big, then what we end up with is that Rn, R subscript n rather, is significantly less for 10,000 than for 2, because R divided by 10,000 is a much smaller number than R divided by 2. Therefore, we know that Rn decreases. Now consider changing n, so that's our first argument. N equals 2 versus n equals 10,000 gives Rn decreasing. Then, in order to consider how Rn is decreasing, we can consider an example where we try n from 2 to n to 3, and then consider n to 3 to n to 4. So if we do n as 2, 3, 4, and then we have Rn, we can see that this is given by R over 2, R over 3, and R over 4. So in this case, we're not decreasing linearly because the relationship is not a straight line. Instead, if we were to plot this on a graph, which I will do up here, then what we can see is that for different values of n versus Rn, what we have is, say n is 2, or rather, let's make our graph as accurate as possible. N is 2, 3, 4. What we have is like that, and like that. So this, rather like that. So this is not a straight line, but in fact a curve. Therefore, what we see is that this is not a linearly decreasing graph. Therefore, our answer is that Rn decreases non-linearly, since this is non-linear, as n increases, since n has increased and Rn has decreased. Therefore, our answer is B. Note that one can also recognize this relationship as inversely proportional, which is a non-linear relationship, and save yourself the trouble of having to figure it out for drawing the graph. This question is about resistors in parallel and resistivity. The question says, the table shows the resistivity, length, and cross-sectional area of wires P and Q. So in the table we have wire P of resistivity ρ, length L, and cross-sectional area A, wire Q with resistivity ρ over 4, the same length L, and the cross-sectional area A over 2. We're told that the resistance of wire P is R. And the question wants to know, what is the total resistance of the wires when they are connected in parallel? In order to answer this question, we first need the resistances of the wires and then we need to combine in parallel. To do this, we can use the equation which relates resistivity, for example for wire P, to the quantities given in the table, namely that for P, we have that R is given by rho L over A. We can now perform the same calculation for Q, where we say that the resistance of Q, where I'm going to give all quantities relating to Q a subscript of Q, rho Q, LQ divided by AQ, where we'll replace these with the values in the table. So that's equal to rho divided by 4 multiplied by L on the top divided by A over 2 on the bottom. So RQ is equal to rho times by L divided by 2A, which is just equal to R, the resistance given to us in the question, divided by 2. So now we've calculated the resistance of Q, we need to combine the two resistors in parallel. We can do this by using the equation for the total resistance, RT, as 1 over RT is equal to 1 over RP, which is just R, plus 1 over RQ. Substituting in the values of RP and RQ, we have RP is R, so 1 over R, plus 1 over RQ, which is 1 over R divided by 2, which is equal to 1 over R plus 2 over R is equal to 3 over R. Therefore, if we flip this equation, then what we find is that by taking the reciprocal, the total resistance RT is equal to R divided by 3. Therefore, the correct answer is B. This question is about circuits and the potential divider. The question says, the circuit shown is used to supply a variable potential difference to another circuit. And so we see a 6-volt supply connected in series to a 5 ohm resistor, connected in series to a 10 ohm resistor, and somewhere along that resistor there is a contact place such that you get a variable potential difference across that and the end of the resistor, and that potential difference is what the other circuit is going to get. The question then says, which graph shows how the PD supplied, V, varies as the moving contact C is moved from position P to position Q? And so we have 4 graphs, A, B, C, and D. In order to figure out this question, we first need to determine what the potential difference across the 10 ohm resistor is. We can then break that down and see what that implies for the potential difference that you see across these 2 contacts here. To do that, we need to use Ohm's law. So we need to use the total potential difference across both resistors. So this comes from the voltage law. It's just 6 volts. And so the Ohm's law for the entire circuit says that V is equal to IR, where R is the total resistance in the circuit. So we have that 6 is equal to the current in the circuit multiplied by 5 plus 10. It's only 5 plus 10 because these 2 resistors are in series, so their resistance is at. Therefore, we have that the current in the circuit is equal to 6 divided by 15, which is equal to 0.4 amps. From there, we can work out the total we can work out the voltage across the 10 ohm resistor. Using V equals IR, where we just use the resistance of the 10 ohm resistor now and use the fact that the current is 0.4 amps. V is equal to 0.4 times 10, which is equal to 4 volts. So that's the total potential difference if I were to place a voltmeter like this. Then this would give us 4 volts. As it happens, we're also dealing with this idea of having the contact attached to the resistor at some point, which is going to affect how much voltage we get. To see that, the way to consider this is to consider breaking down the resistor into 2 parts. So the resistance is proportional to the length of the resistor. This comes from the equation resistance is equal to the resistivity multiplied by the length of the resistor divided by its area, and we take the resistivity to be the same throughout the resistor and the cross-sectional area to not change. Therefore, the resistance is just proportional to the length. So the potential difference dropped before the contact will depend on how far along the contact is along the resistor. Consider the contact on the side at Q and on the side at P. If the contact is at Q, then we expect to see the potential difference across the whole resistor, so we expect to have 4 volts. Whereas if the contact is at P, then there's none of the resistor between P and the other contact, so therefore there is no volts dropped across that gap. Therefore, we have 0 volts. So what we expect then is that we have 4 volts whenever the contact is at Q, 0 volts whenever the contact is at P. Therefore, we automatically know that A is no good and B is no good because they start with 6 volts at P and 6 for both of them. So these are no good. We then need to discern between C and D. So D has 0 volts at P, which is okay, but only goes to 2 volts at Q. So this is no good. This means that the only possible answer would be C, which goes from 0 to 4 volts. We can verify this by noting that it has to be a straight line relationship because the resistance that you have a voltage drop across, which goes to the variable potential difference, is proportional to the length of the resistor between the contacts. Therefore, if there's no length of the resistor between the contacts, say at P, then we expect no voltage, and we expect it to linearly increase as we get more and more of that length of that resistor between the 2 contacts, until eventually you're at Q, and whenever you're at Q, you've got the whole length of the resistor, so you have 4 volts. That verifies that our answer should be a straight line, and that it fits the characteristics we've demonstrated throughout the question. So the answer is C. This question is about resistors. The question says, in this resistor network, the EMF of the supply is 12 volts and it has negligible internal resistance. What is the reading on a voltmeter connected between points X and Y? In order to solve this question, it is best to think of the 2 different branches as loops. Specifically, that I start with 12 volts, and as I go around, say, this loop, the loop containing X, or this loop, the loop containing Y, I have to use up 12 volts. So in other words, 12V used up. So our strategy is going to be to calculate how much of the potential difference is being used up between the edge of this parallel combination and X, and the same for between the edge of the parallel combination and Y, and then subtract how much potential is left. Okay, so let's consider the branch for X first. So in order to actually do that, what we need to do is figure out the current in branch X, and then use that to figure out the potential difference that's across the 2 ohm resistor, because that will tell us how much is left from our 12 volts. So if we do that, then the current can be found using Ohm's law. Specifically, we have that 12 volts, the current in the branch, we have 12 volts is equal to the resistance of the branch, which is 2 ohms plus 1 ohm multiplied by I. So 12 volts is equal to I times R. So this is Ohm's law. So then we find that by dividing 12 volts by 3 ohms, we get I is equal to 4 amps. This means that the voltage drop across X, but voltage drop before X rather, is the voltage across the 2 ohm resistor. So what we have then is that the voltage across the 2 ohm resistor, using Ohm's law, is just given by the product of the current through that resistor and its resistance, or 2 times 4, which gives us 8 volts. Therefore, the voltage remaining is just 12 minus 8 is equal to 4 volts. So there are 4 volts left. So potential at X is 4 volts. We can now do the same for the branch involving Y. So the current in the branch, we get using Ohm's law as 12 volts is equal to the total resistance in the branch multiplied by the current. So in this case, it's 3 plus 1. So just a quick statement of Ohm's law. So 3 plus 1 times by I. So I is equal to 12 divided by 4, which is 3 amps. Similarly, the voltage drop before X, or before Y, is the voltage across the 3 ohm resistor. So it's the voltage we're dropping across this guy. So we're using up some of our 12 volts as that voltage is dissipated inside the resistor. So the voltage drop across 3 ohm resistor. So then, using Ohm's law again, we can say that the voltage across the resistor, across the 3 ohm resistor, is equal to 3 times by 3 is equal to 9 volts. So the voltage remaining at Y, if we take this away from 12, because that's how much we're left with to dissipate across the 1 ohm resistor, is given by 12 minus 9 is equal to 3 volts. So the potential at Y is 3 volts. So for the final step then, if we connect a voltmeter here, just to run my diagram, sorry. So what the voltmeter is going to do is it's going to take the potentials at the 2 points it's connected to and subtract one from the other. Therefore, it's going to take the potential at Y and subtract it from the potential at X. So voltmeter subtracts V at X, V at Y rather, from V at X. Therefore, the potential difference between the two is equal to 4 minus 3, which is equal to 1 volt. Therefore, the answer is B. This question is about circular motion and forces. The question says, a bob of mass 0.5 kilograms is suspended from the end of a piece of string 0.45 meters long. The bob is rotated in a vertical circle at a constant rate of 120 revolutions per minute. What is the tension in the string when the bob is at the bottom of the circle? To do this question, it is helpful to consider a diagram of the forces acting upon the bob. If we draw this diagram, then what we can see is that we have the string pulling upwards in order to try and pull the bob around the circle. So we have tension, which I'll label T, going upwards, and we have its weight acting downwards, which is W, which is equal to mg. And we're told the mass, and we know that G is 9.81. We also know that the bob is moving in a circle. The force required to keep an object rotating in a circle is given by F is equal to m times omega squared times by r. This comes from Newton's second law. Which says that for an object with a constant mass m, the acceleration is just proportional to the force. So the resultant force acting on the object is equal to the product of the object's mass and its acceleration. We also use that to keep an object in a circle, an object moving in a circle, we have that A is equal to omega squared. So omega is the angular speed of the object multiplied by r, where r is the radius of the circular path that the object is moving in. So this is where this equation comes from. And we know that since this bob is moving in a circle, at all times the resultant force acting upon it must be m times omega squared times by r. So that means that we can convert this force diagram into an equation like so. So the resultant force, F, is equal to m times omega squared times by r, which is equal to the tension minus the weight, like so. Then we can rearrange this and get that T is equal to mg plus m omega squared r. Now we need to identify what these quantities are. So the length of the string, 0.45, is the radius of the circle. We're shown that in the diagram. So this is r. 120 revolutions per minute is omega, but it's not in the units that we'd like to use, since all our quantities have to be in SI units before we can put them into equations. In order to do this then, we'll need to convert 120 revolutions per minute into radians per second. To do that, we say that if there are 120 revolutions per minute, then since there are 60 seconds in a minute, we can divide 120 revolutions by 60 to get the number of revolutions per second, and then multiply that by 2 pi to get the angle rotated through per second in radians. So in other words, because we've calculated that there are a certain number of revolutions per second and each revolution is an angle of 2 pi, when we multiply these together, we get the number of radians per second. So in other words, this is 4 pi radians per second. It's okay to keep this as it is because it's an intermediate answer. So then we can also identify the mass, which we're given. So that's m up here. G, we know, is 9.81 meters per second squared. So now we can put these values into our equation for T. And what we find then is that T is equal to factoring out the m, G plus omega squared r, like so, which is equal to 0.5 multiplied by 9.81 plus 4 pi all squared from up here, multiplied by the radius, which is 0.45. And when you do that, you end up with 40.435 and so on, which is about 40 newtons. Therefore, the answer to this question is D. This question is about simple harmonic motion and energy. The question says, which graph best shows how the kinetic energy of a simple pendulum varies with displacement from the equilibrium position? In order to answer this question, we need to use the fact that the pendulum is undergoing simple harmonic motion. In simple harmonic motion, there is an equation that relates the speed of the object to its displacement from the equilibrium position. That equation is V is equal to omega multiplied by the square root of a squared minus x squared. This equation says that V is equal to the frequency of oscillations of the object undergoing simple harmonic motion multiplied by the square root of the amplitude all squared. So the amplitude is just the maximum displacement from the equilibrium position of the object minus the displacement of the object from the equilibrium position x, and that's all squared as well. So this displacement from the equilibrium position will change based on where the object is, and that's what is on the x-axis of all these graphs. Since the quantity that we're interested in is kinetic energy, it makes sense to try and look for an equation that relates the velocity of an object to its kinetic energy. This equation is given by kinetic energy the speed, sorry. The kinetic energy, EK, is equal to 1/2 times the mass of the object times by the velocity squared. So objects with a larger mass have a larger kinetic energy if they're moving, and objects with larger speeds have a larger kinetic energy as well. So if we substitute this equation for the speed into here, then what we find is that the kinetic energy is given by 1/2 times by m times by omega all squared times by a bracket of a squared minus x squared. This equation then represents how the kinetic energy changes with the displacement of the object. We can then apply that and compare each of our graphs to see which one this most closely resembles. In order to do this, we should identify that this is a quadratic graph because it has an x squared in it, and x squared is the highest power of x. We can also use that it should be an N shape. This is because the sign in front of the x squared is negative. So this means that for example, if the object is at the equilibrium position, then x is 0, then the kinetic energy has its maximum possible value. This corresponds with the velocity being the largest in magnitude as it moves through the equilibrium position. And then as it gets closer and closer to the amplitude, the kinetic energy gets smaller and smaller and smaller. So we have to go from larger values to smaller values. This decrease in the kinetic energy makes sense, because if the object is at the amplitude, then the object is also not moving at that point, as it is about to change direction and move back towards the equilibrium position. Since this is true whether the displacement is positive or negative, and squaring either a positive or negative value still gives you a positive value, only at the equilibrium position will the kinetic energy be a maximum. On either side of it, it will be decreasing. Hence, we have an N shape. So this is due to the sign in front of the x squared being a minus sign, like so. So because this is a quadratic graph, we expect that for larger values of x, the kinetic energy changes more rapidly than for smaller values of x. Now we can use this and compare to our 4 options. So A is a straight line on either side. So this doesn't help. This isn't a quadratic graph, this is a linear graph. So therefore A is out. By the same logic, C is also out, note that C is also increasing in kinetic energy as the displacement increases, which doesn't obey our argument that we gave earlier. Thirdly, for B, we have that the kinetic energy is increasing with the displacement, so that's out as well. This leaves us with D, which obeys everything that we said would be required. Specifically, it's a quadratic graph, and it's n-shaped, so it has its maximum at the equilibrium position, which makes sense because that's where the object, the pendulum, is moving the fastest. This question is about simple harmonic motion. The question says, the graph shows how the displacement of a particle performing simple harmonic motion varies with time. And so we have a graph where we start at the maximum displacement, we go through 0, we go to a minimum, we go back up, and then we eventually end up at the maximum again. The question then says, which statement is not correct? And it gives us 4 to choose from. In order to do this question, it's helpful to consider what the particle is doing at each of the points that it wants us to consider, i.e. t over 2, 3t over 4, and t over 4, which I will label 1, 2, 3, and 4. So let's take 1 first. What we see then is that at t over 4, the displacement is at 0. So I'm going to mark on a line here, which is the equilibrium position, and this will be the same for all diagrams, and the dot represents the particle. I'm also going to mark on another 2 lines out here, dotted lines, which represent the negative maximum amplitude and the positive maximum amplitude. In other words, the maximum displacements from the equilibrium position in either direction. Okay, so at 1, what we have is that the particle is moving through the equilibrium position towards minus A, because we started at the maximum displacement, and we're now going to the maximum negative displacement when we end up at 2. Therefore, we would expect, without looking at the graph, that the speed would be greatest, because we're not moving at A, we're not moving at minus A, so we must speed up as we go through the equilibrium position and then slow down again as we get to minus A. We can see this directly from the graph, because if we look at the graph at t over 4, we should consider the properties of the displacement time graph, specifically that the gradient of the displacement time graph is the velocity. So v is equal to delta s, so s is the displacement, divided by delta t, and t is the time. So what that means then is that at the places where the gradient is the largest in size, whether it's positive or negative doesn't matter, because we're talking about the speed here, that's where we'll expect the speed to be the largest. So therefore, the gradient is largest at this point because this is where the graph is steepest. So in other words, graph is steepest here. And also at 3t over 4. Therefore, at t over 4, the speed of the particle is at a maximum, so it can't be A. Part B says, the potential energy of the particle is 0 at 3t over 4. In this, it's useful to consider the energy transfers. So in this question, what we have is the particle moving from A to minus A, going through the equilibrium position. At the amplitudes, it has the maximum amount of potential energy, and then this potential energy is converted back into kinetic energy as the particle moves through the equilibrium position. So therefore, at the equilibrium position, where the particle is moving fastest, it must have the maximum amount of kinetic energy. Therefore, using the fact that energy is conserved, all of the potential energy that the particle had at A must be converted into the kinetic energy it has at the equilibrium position. So this is no good. So B is also out. And so just to show that on our diagram, if we're going minus a to a, or sorry, this is 0.3, not 0.2, sorry. Then what we have is the particle going this way. So it has no potential energy. All has been converted into kinetic energy. Okay, let's look at option C now. This says the acceleration of the particle is a maximum at time t divided by 2. So let's draw a quick diagram showing the particle at t over 2. So in this case, and this is number 2, what we end up with is the particle furthest away from the equilibrium position at minus a. So now at this point, remember that the particle is not moving, so it's just sitting at minus a. It's about to come back, but at this point it cannot, because its velocity is 0. So then we can use what we know about simple harmonic motion, which is that in simple harmonic motion, the acceleration of the particle is equal to minus the rate of oscillations of the particle squared multiplied by its displacement from the equilibrium position. Now, since x is equal to minus a, we have the largest value of the acceleration here. In other words, a is equal to omega squared big A. So what this means then is that because the particle is at its amplitude and it says it is at its negative amplitude, it's going to be pulled with the maximum possible acceleration back towards the equilibrium position, which is also at this point towards the positive amplitude. Therefore, what we see is that we actually have the maximum amplitude here. If it was on the other end, i.e. in position 4, which we'll talk about in a second, it would have the minimum possible acceleration, since it would have the largest negative possible value of the acceleration. But anyway, this one's out. This leaves us with D, which says the restoring force acting on the particle is 0 at time t. So let's draw a diagram of where we are at t. So on the graph, this is when we're at the maximum possible displacement. So we're at big A. Like so. And so we need to consider the forces that act upon the particle during this process. So whenever the particle's at the equilibrium position, it's not being pulled towards the equilibrium position because that's where it naturally wants to sit. The reason that it's oscillating is because we pulled it away to begin with, and then a restoring force pulls it back towards the equilibrium position. So therefore, what we see is that as we get further and further away from the equilibrium position, the restoring force also increases. So too does the restoring force. The size of this restoring force can be calculated using Newton's second law. F is equal to ma, the resultant force acting on the particle, is equal to its mass multiplied by its acceleration. So this is because the particle has a constant mass, which is going to be given to us by minus m omega squared x. So what we see then is that as long as we're away from the equilibrium position, we must have a restoring force. Therefore, D is incorrect. Thus, the correct answer is D, because this is the only statement which is incorrect.